Welcome, and thank you for joining us. You, the learner, are stepping into another highly customized deep dive today, but I really need to set expectations right out of the gate here.
Yes, definitely.
Today's journey is not a casual surface-level summary. We are not doing the typical bird's eye view of a topic. Today, we are embarking on an epic, almost microscopic exploration of a single, profound mathematical mystery.
Microscopic is the right word for it.
We're going to be examining a definitive, highly dense source text titled The Secret of the Covariant Derivative of Tensors and its Minus Sign. And our mission, the entire reason we are sitting here today with you, is to answer two highly specific questions that lie at the very beating heart of general relativity and differential geometry.
Right.
First, why does the covariant derivative of a tensor have two Christoffel symbol terms? And second, why on earth does a minus sign appear when differentiating covariant components, which are the ones with the lower indices?
It is, it's a phenomenal piece of source material. And I know right off the bat to you listening, those two questions might seem like the most esoteric mathematical trivia imaginable.
Yeah, totally arbitrary.
Exactly. But I assure you, and I cannot stress this enough, they are the linguistic scaffolding of the universe. To truly understand gravity, to understand space-time, and to understand the literal fabric of reality, you have to understand where that minus sign comes from.
Exactly. And because the stakes are that high, I want to let you know that for this deep dive, we are operating under a specific directive. We're calling it the unabridged protocol.
The unabridged protocol.
Right. What that means in practice is that we are going to proceed in strict linear order through this text, page by page, paragraph by paragraph, formula by formula. We are not skipping the hard parts.
No skipping.
We are going to operate as if we have all the time in the world. If a foundational concept appears that requires a 10-minute detour to fully grasp, we are going to take that detour until the concept is absolutely crystalline.
Furthermore, to make sure we don't get lost in our own enthusiasm, we're going to rigorously check our own understanding as we go. Before we move from one complex concept to the next, we will explicitly pause and verify with each other that we've extracted every possible nuance. We can't afford to leave any conceptual blind spots.
Yes, exactly. And there's one more crucial detail regarding how we handle the math itself. Because this is an audio medium, reading equations can quickly turn into pure chaos.
Absolute chaos, yeah.
So, to ensure maximum clarity for you, we are employing a strict three-part vocalization method for every single formula. First, we'll identify the type of expression. Second, we'll state the raw mathematical structure. And third, we will provide the exact phonetic vocalization. This ensures you know exactly what the math is, what it looks like on the page, and how to say it.
It's the only way to keep the audio clean.
Okay, let's unpack this. We have our mission. The text begins with a massive foundational claim. It states that this minus sign is the essence of modern physics. Why is that mandate so absolute? Why does a single line of algebra hold that much weight?
Well, because without it, the laws of physics would change depending on who is looking at them or how they choose to draw their coordinate grid.
Right.
The entire guiding philosophy of modern physics, especially post-Einstein, is coordinate invariance. Whether you are falling into a black hole, accelerating in a rocket, or floating in completely empty space, the fundamental equations governing reality must remain absolutely true. That minus sign is the mathematical counterbalance that ensures reality doesn't shatter when you change your perspective.
It is, quite literally, the language of the universe maintaining its own consistency.
Precisely.
I love that framing. The language of the universe maintaining its consistency. Before we dive into the history, I just want to make sure we've totally nailed the stakes here. Are we completely aligned on why this deep dive matters before we open the first chapter of the text?
I believe we are. The premise is set. The stakes, which are nothing less than the stability of physical laws, are defined, and the necessity of our meticulous approach is clear. We are ready to begin with the historical background.
Let's do it. So, Chapter 1. The text starts us off in the 17th century exploring Leibniz's dream. It deconstructs the origins of calculus with Gottfried Wilhelm Leibniz and Isaac Newton.
Right, the founders.
Now, back then, calculus was revolutionary, but it was built on a massive assumption. A derivative simply meant finding a slope or a tangent line on flat paper, what mathematicians call Euclidean space. But the text highlights a paradigm-shifting question that emerged later. What if we live on a curved surface?
That changes everything.
Let's take a deep digression right here. I want to really contrast these two ideas. What does a derivative actually mean on flat paper versus the conceptual leap required to even think about measuring change on a curved surface?
It's a fundamental shift in how you view the stage where physics happens. On flat paper, Cartesian space, calculating a derivative is incredibly straightforward because your grid lines, your x and y axes, never ever change direction.
Right.
If you draw an arrow pointing up and slide that arrow anywhere on the paper, up is still the exact same absolute direction. The background space is completely passive. It's an inert, unchanging stage. So when you measure how a function changes, when you calculate its slope or derivative, you are only measuring the function itself.
Right, because the paper isn't doing anything tricky behind your back. The paper is perfectly reliable.
Precisely. The paper is rigid. But the text asks us to imagine taking those same measurements on curved surfaces, like the outside of a sphere or a saddle. This was Leibniz's underlying, albeit unrealized, dream to generalize the mathematics of change to any geometry.
So think about being on the surface of a sphere, like the Earth.
Yes, think about what a straight line even means there. What does parallel mean? If you stand at the equator, point an arrow straight north, and physically slide that arrow along the surface all the way to the North Pole.
The concept of north fundamentally twists.
Exactly. It twists as the geometry of the space curves underneath it. The conceptual leap here is realizing that the derivative, the measurement of change, must now account for two entirely different things simultaneously.
The object and the stage.
Right. The change in the actual object you are studying, or the twist of the stage it happens to be standing on.
Okay, that is a brilliant way to picture it. The stage itself is twisting, so if you just measure the object, your data is contaminated by the stage. I want to linger on this for just a second because it's so foundational. If I measure the wind blowing across a flat map and the wind speeds up, standard calculus captures that perfectly.
Perfectly.
But if I measure the wind blowing across a globe, standard calculus might tell me the wind changed direction, when in reality the wind went perfectly straight, but the globe curved.
Standard calculus is completely blind to the curvature of the stage. It assumes the stage is flat. When the stage is curved, standard calculus gives you an answer that is a tangled mess of the object's real behavior and the stage's hidden curvature.
A tangled mess. Okay, so for our completeness check, do you feel like we've fully captured Leibniz's dream and that crucial distinction between flat and curved space derivatives? Have we left any stone unturned there?
I think the foundation is solidly laid. The necessity for a completely new kind of mathematical tool has been firmly established. We can trace how that tool was slowly built, starting in 1827.
Which brings us to Carl Friedrich Gauss and his Theorema Egregium. The text translates this from Latin as the remarkable theorem. Here's where it gets really interesting. Gauss proved that you could measure the curvature of a surface entirely from within it, which gave birth to intrinsic geometry.
Intrinsic geometry, yes.
Let's really put you, the learner, into this concept because it's completely mind-bending. Imagine you are a two-dimensional creature. Let's say an incredibly smart, perfectly flat ant living entirely inside the rubber surface of a curved balloon. Why can't this ant just use normal 3D tools to figure out its world is curved?
Because the third dimension literally does not exist in the ant's universe. As that 2D ant, you have no conceptual framework for up or down relative to the balloon's surface.
You can't just look up.
No, you cannot step off the balloon, float in the air, grab a 3D ruler, and say, ah, yes, looking at my universe from the outside, I see it is curved into a sphere. Your entire physical reality, your light, your forces, your matter, it is all confined strictly to the rubber of the balloon. What Gauss's remarkable theorem proved is that this ant doesn't need a third dimension to know its world is curved.
Wait, how is that possible? If you can't step outside the universe to look at it, how do you know it's not flat?
By doing local geometry and seeing if the rules of flat space fail. For instance, the ant could draw a giant triangle on the surface of its balloon universe. In flat Euclidean space, the interior angles of a triangle will always, unconditionally, add up to exactly 180 degrees.
Basic geometry.
But if this ant uses a protractor to measure the angles of a massive triangle drawn on the balloon, they might add up to 200 degrees, or 250 degrees. Or the ant could tie a string to a post, walk out a certain distance, let's call it the radius, r, and walk in a circle.
And measure the circumference.
Exactly. In flat space, the circumference is strictly 2 times pi times r. On a sphere, the circumference will be less than that. The geometry of the space itself betrays its curvature. You don't need to look at the universe from the outside. The curvature is intrinsic to the space itself.
That is profound. The curvature is baked into the distances and angles themselves, but the text points out a limitation here. Gauss figured out how to measure the curvature of the stage, but what was he missing?
He was missing the calculus. Gauss could tell you the balloon was curved and exactly how curved it was at any point. But he still lacked the ultimate mathematical machinery to properly differentiate vectors, like the velocity of another ant running across the balloon as they move through this inherently curved landscape.
So he could measure the shape, but not the movement across the shape.
Right. He had the geometry, but he didn't have the dynamic calculus to track movement across it without the coordinate system messing up the results.
He had the map, but not the compass to navigate the changing winds on that map. All right, completeness check. Before we leap forward to a student, do we feel completely confident that intrinsic geometry is fully fleshed out for you, the listener?
Yes. The idea that curvature can be experienced and measured strictly from within the space without referencing a higher dimension is the prerequisite for everything that follows. We can move to 1854.
All right, moving to 1854. Bernhard Riemann's revolution. Riemann was actually Gauss's student, and he takes his teacher's work to an entirely new level with the concept of the Riemannian manifold. The text introduces a critical mathematical object right here, and we need to utilize our pronunciation protocol to get it on the table.
Absolutely. This is the cornerstone object, the metric tensor Mutlunu.
Okay, G sub mu. So what does this all mean? The text refers to the metric tensor as a ruler that dynamically changes its length depending on where you are in space. We need to unpack this thoroughly. Explain to me how a ruler can change its length.
Think of the metric tensor, G sub mu, as the ultimate, localized instruction manual for measuring distance. In flat space, we have the Pythagorean theorem a squared plus b squared equals c squared. That formula is a global rule.
It works everywhere the same way.
Right, it tells you exactly how to convert coordinate numbers on a graph into physical distance, and it works identically everywhere. But Riemann asked, what if we are in a manifold, a space of any number of dimensions that can curve, warp, stretch, and squish wildly from point to point?
A space where the paper isn't just curved like a sphere, but warped like a funhouse mirror.
Exactly. In a space like that, a single global rule, like the Pythagorean theorem, is useless. The metric tensor replaces it. The metric tensor tells you, at one specific, microscopic, infinitely small point in space, exactly how to convert your coordinate numbers into physical distance. Because the space is warped, this ruler must adapt locally.
Let's make this tangible for the learner. Imagine a giant map of the Earth spread out on a table, like a standard Mercator projection. We all know that projection heavily distorts things near the poles, right?
It does.
Greenland looks massive, almost the size of Africa, even though in reality, Africa is about 14 times larger.
That is a perfect analogy. If you have a coordinate grid laid over that map, a 1-inch grid box at the equator represents a very different physical distance than a 1-inch grid box up in Greenland. If you just count the grid boxes, your measurement of distance is completely wrong.
Because the boxes mean different things in different places.
You need a conversion factor that updates depending on where your finger's pointing on the map. The metric tensor is that dynamically updating legend. It encodes all the squishing and stretching of the coordinate system. It tells you, you are in Greenland now. Multiply your grid box count by this tiny fraction to get the true physical distance.
So the metric tensor is the localized translator between the arbitrary grid we draw and the physical reality of the space.
Okay, I think that analogy really grounds it. Let's do a completeness check. Does that fully satisfy the introduction of the metric tensor and Riemann's manifold?
The analogy holds perfectly. The concept of the dynamically updating ruler is secure. Riemann gave us the localized ruler, but someone still had to figure out how to do calculus while holding a ruler that keeps changing. Which brings us to 1869. 1869. Elwin Bruno Christoffel and the Birth of Symbols. The text introduces Christoffel's quest. His goal was to fix the messy, chaotic changes in coordinate systems that naturally occur when you try to calculate derivatives across these warped Riemannian manifolds. This introduces our next crucial piece of mathematics. Let's get the notation established.
This is the centerpiece of our deep dive. The Christoffel symbol, or affine connection, gamma lambda mamma, with upper index lambda and lower indices mu and nu.
Capital gamma with upper index lambda and lower indices mu and nu. Okay, here's the core question. Why is this specific symbol needed? The text refers to it as a correction term designed to cancel out the chaos of a shifting coordinate system. Break down that chaos for us.
Let's connect this back to Riemann's shifting ruler, the metric tensor. Because the ruler is shifting depending on where you are, the coordinate grid lines that you draw in your space are inherently curving, converging, and diverging. Now imagine you are a physicist trying to measure how a vector, say the momentum of a particle, is changing as it moves through this space. You take your standard derivative, You measure a change.
Okay, I have a measurement.
But here's the catastrophic problem. You don't know if the vector actually changed or if your coordinate grid simply twisted underneath it.
It's the wind on the globe problem again.
Exactly. Your measurement is going to pick up artificial noise. You will measure a numerical change in the vector's components, but a huge fraction of that measurement might just be the coordinate grid warping. Christophel's absolute genius was realizing that you could mathematically isolate that noise.
He found the noise.
Capital Gamma, with upper index lambda and lower indices mu and nu, is the mathematical embodiment of that isolation. It literally quantifies exactly how much and in what direction the coordinate grid is twisting at one specific microscopic point.
So it's like a calibration tool. If I am on a ship rolling on the ocean and I am trying to measure the trajectory of a ball thrown across the deck, I need to know exactly how much the ship is rolling at every millisecond so I can subtract the ship's movement from the ball's movement.
That is exactly what it is. Christoffel figured out how to measure the roll of the ship, the twisting of the metric tensor, and packaged it into this symbol. By knowing exactly how the grid twists, you can subtract that artificial twist from your derivative measurement, leaving you with the pure, true, geometric change of the vector itself.
He quantified the noise so it could be surgically deleted from the equations. That is staggering. Let's pause for the completeness check. Are we solid on the fundamental purpose of the Christoffel symbol before we look at how it was finally integrated into modern math?
We are. The motivation for the symbol, as a calibration tool to delete coordinate noise, is deeply established. We can move to the culmination of this historical journey in 1900.
1900 brings us to Gregorio Ricci-Crabastro and Tullio Levi-Civita. The text outlines their monumental achievement, the finalization of tensor calculus, which at the time was called absolute differential calculus. The text highlights their core governing principle. If a physical quantity is a tensor, its derivative must also be a tensor, completely immune to coordinate transformations.
This is where we reach the philosophical bedrock of modern physics. Ricci and Levi-Civita formalized a demand that the universe must make sense regardless of human maps. A physical truth cannot depend on the arbitrary grid we choose to overlay on it.
Right.
Let's use our wind vector again. If you have a physical vector representing the wind, and you arbitrarily decide to change your map from a square Cartesian grid to a circular polar grid, the actual physical wind didn't suddenly blow in a different direction.
Right. The wind doesn't care about my map.
Exactly. Therefore, the mathematical object representing the wind, and crucially, the mathematical object representing the wind's acceleration, its derivative, must smoothly and perfectly transform to the new grid without breaking or generating nonsensical noise. Ricci and Levi-Civita took Christoffel's symbols and built the rigorous, unbreakable rules for how to actually do this.
Put the pieces together.
They took Gauss's realization of intrinsic curvature, Riemann's metric tensor, and Christoffel's correction symbols, and assembled them into the final engine tensor calculus.
Okay, that brings us to the end of the historical narrative portion of the text. I want to take a breath here and run our completeness check. We've traced a massive 70-year mathematical evolution, from Gauss realizing we can measure curvature from the inside, to Riemann building the dynamically changing ruler, to Christoffel isolating the noise of the twisting grid, and finally, Ricci and Levi-Civita building a calculus that is immune to that noise. Does that lineage feel complete? Have we missed any critical stepping stones?
I believe we have thoroughly excavated the history. We understand the why behind the math before we've even looked at the deep algebra. The historical and motivational foundation is absolutely solid. We are now prepared to dive into Chapter 2, the foundation concepts of vectors and tensors.
Fantastic. Let's get into the mechanics. The text states that before we can derive this unbreakable covariant derivative, we have to sharpen our tools. It introduces two fundamentally different types of vectors, contravariant versus covariant vectors. The names alone are notoriously intimidating. Let's break down the first type. Let's get the notation and the transformation rule for a contravariant vector.
Following the protocol, the contravariant vector v-nu v-bler with upper index mu, and its crucial behavior under a change of coordinates. The transformation rule v-nu prime with upper index mu equals the partial derivative of x prime with upper index mu with respect to x with upper index nu times v with upper index.
Okay, stop right there. The text explicitly points out that contravariant vectors, like velocity or physical displacement, transform directly with coordinates. It gives an example. If a coordinate grid doubles in its density, the vector component doubles. I really want to dig into this. I am going to push back here because intuitively this sounds wrong.
It trips a lot of people up.
If I have a physical arrow representing my speed and I zoom in on my map so the grid lines are tighter, My actual physical speed didn't increase, so why does the number representing the vector go up?
It is a fantastic question, and it's where the intuition usually breaks down. It comes down to separating the physical object from the numbers used to describe it. Think of a contravariant vector as a literal physical arrow floating in space. It has a definite unchanging length. Let's say you draw this arrow on a piece of graph paper, and the arrow happens to be exactly the length of one single grid block. Its component is 1.
Okay, arrow is 1 block long.
Now, suppose someone changes the map. They zoom in so that the physical distance that used to be covered by 1 block is now represented by 2 smaller blocks. The grid has doubled its density.
Okay, I have my zoomed-in map. The grid lines are closer together.
Look at the physical arrow on this new map. The arrow itself did not grow or shrink. But to describe that exact same physical arrow using the new map's language, you have to say it spans 2 blocks. The coordinate number you write down changed from 1 to 2.
Oh.
The numerical components of the vector scale directly with the density of the coordinates. If the grid density doubles, the numerical components must double to represent the exact same physical reality.
Okay, I see it now. The arrow stays the exact same physical size, but because the grid markings shrunk, the number of grid markings it pierces through goes up. It varies with the coordinates. That is why the transformation rule uses the direct partial derivative of the new coordinates with respect to the old coordinates. It's a direct scaling factor.
Precisely. It scales directly. That is the essence of a contravariant vector, an upper index vector.
Let's do a completeness check on that. Do you feel like that clears up the contravariant side of the equation?
I believe so. It is a measurement of displacement across a grid, so it scales with the grid's frequency. We are clear to examine its mirror image.
Excellent. Now for the other side of the coin, let's establish the covariant vector.
A covariant vector A with lower index mu, and its corresponding behavior when changing coordinates. The transformation rule A prime with lower index mu equals the partial derivative of x with upper index nu with respect to x prime with upper index mu times a with lower index nu.
Notice the fraction flipped. The text emphasizes this. Covariant vectors, like gradients, transform inversely. If the grid density doubles, the component of the covariant vector halves. Explain this inverse relationship. Why is a lower index vector tied to this completely opposite behavior?
Think very carefully about what a gradient represents physically. It is not an arrow of displacement piercing through space. It is a measurement of steepness, a rate of change, or a density. Let's use the analogy of a hill. You are a surveyor, and you are measuring the slope of a hill. On your current map, you find the hill rises 10 meters for every 1 grid block you walk horizontally. The gradient component is 10.
Okay, slope is 10 meters per block.
Got it. Now, perform that exact same coordinate change we did earlier. Zoom in so your new grid blocks are half the physical size. The grid density is doubled. You take 1 step across this new, smaller grid block. Because the block is physically shorter in the real world, you haven't walked as far, so you only rise 5 meters. The number representing the slope per block has halved. It went from 10 to 5.
Oh, wow. Even though the grid frequency doubled, the vector's numerical component shrunk by half.
Exactly. It varies inversely to the coordinate change. The physical hill didn't change steepness, but because your unit of horizontal measurement got smaller, the amount of vertical rise packed into that unit also got smaller. That is why the transformation rule uses the inverted fraction, the partial derivative of the old coordinates with respect to the new coordinates. It scales inversely.
That is an incredibly helpful way to visualize it. A contravariant vector upper index is an arrow piercing through grid lines. A covariant vector lower index is like measuring the density of the grid lines themselves. One stretches with the grid, the other shrinks. Let's pause for the completeness check. Are we confident we have thoroughly unpacked contravariant versus covariant? Because the text leans heavily on this distinction.
The distinction is critical, and I think contrasting the displacement arrow with the gradient slope clarifies it perfectly. Upper index transforms directly, lower index transforms inversely. We are ready to define a tensor.
The text moves to clarify what is a tensor. It explicitly states that tensors are not just matrices, but geometric objects that obey strict transformation rules. Let's get the notation for a couple of tensors down.
The 1-1 tensor, tensor T, with upper index mu and lower index nu. This tensor has 1 contravariant component and 1 covariant component, and a second type. The 0-2 tensor T with lower indices, mu and nu. This tensor is purely covariant with 2 lower indices.
The key takeaway the text drives home here is that a tensor is defined entirely by how it transforms. A matrix is just a dumb spreadsheet, an array of numbers. But a tensor is an array of numbers that is tightly bound to a coordinate system, demanding that if you change the system, every single number in that array updates according to those exact direct or inverse partial derivative rules we just spent time exploring.
That's right.
Every upper index multiplies by a direct derivative. Every lower index multiplies by an inverse derivative.
That is the defining feature. If it doesn't transform that way, it isn't a tensor. It's just a meaningless array of numbers that will break the laws of physics if you try to use it in an equation.
Okay, let's take a breath. Completeness check. We have established our tools, we understand the different types of vectors, and the strict transformation demands of a tensor. Have we left anything unsaid regarding these foundational concepts before we get into the actual crisis of calculus?
The foundation is securely set. The stage is primed for the central mathematical conflict of the text in Chapter 3.
Here we go. Chapter 3, the crisis of ordinary derivatives. The text uses a relatively simple 2D example to show why the standard derivative completely breaks down and fails the tensor transformation test. It contrasts Cartesian coordinates, x and y, with polar coordinates, r and theta. Let's deconstruct this visually for the listener. Explain deeply how basis vectors and polar coordinates continuously change direction.
Let's start with the familiar. Imagine you are standing on a slat, infinite Cartesian plane, like a giant piece of graph paper. The x basis vector is a tiny arrow that always points dead right. The y basis vector is a tiny arrow that always points dead up. It doesn't matter if you are standing at the origin or if you walk 1,000 miles away. Right is always right, and up is always up.
The compass always points in the same direction.
Exactly. The basis vectors are completely static and uniform. But now, throw away the graph paper and switch to a polar coordinate map. Your position is no longer defined by moving right and up. It is defined by your distance from the center, which we call r, and your angle around the center, which we call theta.
Like a radar screen.
Just like radar. Now, imagine the basis vector for r. This vector always points directly away from the origin. If you stand at the 3 o'clock position on this radar screen, the r vector points directly right. But suppose you walk along a circular path to the 12 o'clock position. Now, that exact same r vector, which still defines moving away from the origin, is pointing dead up. The actual physical direction of the basis vector has rotated 90 degrees just because you changed your location.
So even though space itself is flat in this example, the background grid of polar coordinates is twisting and turning depending on where you stand. I think that perfectly illustrates the danger. Let's do a completeness check. Are we good to dive into the mathematical proof of this failure?
The twisting of the polar basis vectors is the perfect conceptual primer. We are ready to see how this ruins the calculus.
This is the inciting incident of the mathematics in the text. We try to differentiate a vector using standard calculus, but the result is fundamentally broken. It does not transform like a tensor. The text provides a step-by-step derivation of this failure. We're going to take this slowly, line by line, and discuss what is happening. Let's start with the absolute basic premise.
We begin with the attempt at a standard ordinary derivative of a contravariant vector. The ordinary derivative partial nu of v mu, the partial derivative with respect to x nu of v with upper index mu.
Okay, so that's just how much the vector v changes as I move in the new direction. Simple enough. But to test if this is a valid tensor, we have to see what happens when we change our coordinate system from the old grid x to a new grid x prime. To do that, the text applies the chain rule.
The chain rule application, frac partial x nu, frac partial x mod alpha, the partial derivative of v prime with upper index mu with respect to x prime with upper index nu equals the partial derivative with respect to x prime with upper index nu of the quantity. The partial derivative of x prime with upper index mu with respect to x with upper index alpha times v with upper index alpha.
Let's translate that math. The left side is the derivative in our new coordinate system. The right side is where the magic happens. V prime, the vector in the new system, is just the original vector v multiplied by that direct scaling factor we talked about earlier, the partial derivative of x prime with respect to x. Now, look closely at what we're actually taking the derivative of on the right side. It's a product.
Yes, it is.
It's the transformation matrix multiplied by the vector itself. And anytime you take the derivative of two things multiplied together in calculus, you must use the product rule.
The derivative of the first times the second plus the first times the derivative of the second. Expanding via the product rule gives us the product rule expansion, frac partial x nu, equals the partial derivative of x prime with upper index mu with respect to x with upper index alpha times the partial derivative of v with upper index alpha with respect to x prime with upper index alpha times the partial derivative with respect to x prime with upper index nu of the quantity. the partial derivative of x prime with upper index mu with respect to x with upper index alpha.
Okay, we are almost at the catastrophe. To clean this up, the text applies the chain rule one final time to that very first term, essentially splitting the denominators to get the fully expanded final equation. Let's hear the final noise term.
This is the result of the standard derivative undergoing a coordinate transformation. The final expanded noise term, frac partial x beta, frac partial x beta beta,
Yeah.
plus frac partial 2, partial 2 beta frac partial x beta plus v alpha frac partial x alpha equals the partial derivative of x prime with upper index mu with respect to x with upper index nu times the partial derivative of v with upper index alpha with respect to x with upper index beta plus v with upper index alpha times the second partial derivative of x prime with upper index mu with respect to x prime with upper index nu and x with upper index alpha.
Okay, full stop. Let's stare at this massive final equation. The text demands we dissect this. Look at that first big chunk of algebra before the plus sign. That chunk is perfect. It is exactly what a true tensor transformation should look like. It's the original derivative multiplied by clean first-order scaling factors. If the equation ended there, we would be happy.
It would be done.
But then there is a plus sign and an enormous rogue term appended to the end. Why is that second partial derivative term an absolute catastrophe for physics?
Because it ruins the coordinate invariance. To be a true tensor, an object must transform cleanly, using only the first derivatives of the coordinates, those direct scaling factors we discussed. But because the product rule forced us to take the derivative of the transformation matrix itself, we generated a term with a second partial derivative. The second partial derivative of x prime with respect to x prime and x. Think about what a second derivative is in physics.
Right, the first derivative is velocity.
The second derivative is acceleration. This rogue term is literally measuring how the transformation between the coordinate grids is accelerating or twisting across space.
So it's the mathematical signature of the grid curving under our feet.
Yes. Because this extra rogue term is physically appended to our equation with a plus sign, the entire expression fails the tensor test. It does not transform cleanly. If you try to use this standard derivative in a physics equation, the answer you get will change completely depending on whether you use Cartesian or polar coordinates, because the polar coordinates will generate this massive extra noise term and Cartesian won't. The standard derivative is hopelessly contaminated by the curving of the coordinate system.
I want to make sure I really internalize this. It's like I am trying to measure how fast a car is accelerating on a track, but I'm forced to take my measurements from a train running parallel to the track. If my train is moving at a steady, constant speed like flat Cartesian coordinates, I can easily subtract my speed to find the car's speed.
Exactly.
But if my train is wildly accelerating and braking and going around curves like polar or curved coordinates, my raw data of the car's acceleration is completely ruined by my own acceleration. The second derivative term is the acceleration of the train.
That is an impeccable analogy. You have contaminated data. You cannot do physics with contaminated data.
Right. I think we have thoroughly dismantled the standard derivative. Let's pause for the completeness check. We've proven why it fails, and we've isolated the exact mathematical culprit, the second partial derivative noise term. Are we entirely satisfied with this derivation before we look at how to fix it?
The derivation is complete, the crisis is fully established, and the culprit is unmasked. We are ready to introduce the savior.
Which brings us to chapter 4, the savior, the Christoffel symbol. We talked about Christoffel conceptually in the history section, but now we get to see the sheer brilliance of his algebra. The text explains that Christoffel solved this crisis by reverse engineering the noise. He predicted the contamination and built a symbol that generates the exact opposite contamination. Let's see how he defined his symbol.
This is how Christoffel defined the transformation rule for his symbol, capital gamma. Notice what is buried inside it. The Christoffel transformation rule, gamma lambda left, partial sexual, partial external lindo gap plus gamma prime, causal muno, minus the second partial derivative of x prime with upper index lambda with respect to x with upper index mu and x with upper index nu, times the inverse of the partial derivative of x with upper index mu with respect to x prime with upper index mu.
That is incredible. I want the listener to really catch what he did there. Look closely at that formula. The exact same second partial derivative, the acceleration of the grid that completely ruined our calculation a moment ago, is baked right into the fundamental definition of the Christoffel symbol. But there is one crucial life-saving difference. What is sitting right in front of that second partial derivative?
A minus sign.
A minus sign. He engineered a mathematical antibody. He built a symbol that, when transformed, spawns the exact same toxic noise, but natively with a negative sign. Let's do a completeness check. Do you feel like that reverse engineering strategy is clear?
It is elegant in its simplicity once you see the mechanics. It is perfectly clear. We can proceed to formulate the new unbreakable derivative.
The covariant derivative of a contravariant vector. We are now going to combine the broken standard derivative with our newly engineered antibody to create a tool that works everywhere in the universe. Let's state the formula.
The covariant derivative partial nu v plus gamma mu nu v plus gamma mu nu sigma with lower index nu of v with upper index p nu mi equals the partial derivative with respect to x nu of v with upper index mu plus gamma with upper index mu and lower indices nu sigma times v with upper index sigma.
We have arrived at the new derivative, represented by nabla, that upside-down triangle. And here's where I really want to pause and emphasize something that sets up the rest of the text. Look at the operation connecting the standard derivative and the Christoffel term. It is a plus sign. Nabla equals the partial derivative plus gamma times v. I need you to explain exactly why we are adding here. Why is it a plus sign for a contravariant vector?
It's a game of perfect calculated balance. Recall our derivation of the broken standard derivative. The noise term, the acceleration of the grid, was generated as a positive addition to the formula. It was a plus. Now recall Christoffel's antibody. He built his symbol, gamma, so that when it undergoes a coordinate transformation, it natively spawns the exact same noise, but with a negative sign. Therefore, to cure our standard derivative, we must add the Christoffel term to it.
Because adding a negative is a subtraction.
Exactly. The positive noise springing out of the standard derivative meets the negative noise springing out of the Christoffel symbol. They perfectly annihilate each other, leaving zero noise. What you are left with is a pristine coordinate invariant tensor.
It really is mathematical poetry. You add the symbol because the symbol secretly contains the subtraction you desperately need.
Yeah.
All right, completeness check. Before we move into the absolute core of the text, the covariant minus sign, are we confident that we have fully formulated the unbreakable derivative for a contravariant vector?
We have. The covariant derivative with the positive Christoffel connection is conceptually and mathematically secured. This prepares us for the climax of the text. Here we go, Chapter 5, the core, the minus sign secret. This answers the second of our two overarching questions. If the contravariant vector, the upper index, uses a PLOS sign, why does the covariant vector, the lower index, demand a minus sign? The text provides two methods to prove this. We're going to dive deep into Method 1, the Leibniz rule, also known as the product rule. This is going to be an extensive step-by-step mathematical proof. We will take it line by line, conversational step by conversational step. Let's initiate the sequence.
We start by looking at the absolute simplest mathematical object possible, a scalar which has no indices at all. The scalar derivative mob mu phi with lower index mu of phi equals the partial derivative with respect to x mu of phi. Right. Let's think about why this is. A scalar is just a pure number at a point in space, like temperature. 72 degrees. It doesn't point anywhere. It doesn't stretch or shrink. Because it has no direction, it doesn't care if the underlying grid twists or accelerates. Therefore, its covariant derivative, nabla, is exactly the same as its ordinary standard derivative. There is no coordinate noise to correct. So no Christoffel symbol is needed. That is our foundational axiom. What is the next step in the proof?
The next step is a clever mathematical trick. We want to figure out the rule for a covariant vector. We know the rule for a scalar no correction, and we know the rule for a contravariant vector a plus correction. So we artificially construct a scalar by multiplying or contracting a covariant vector and a contravariant vector together. The scalar contraction phi, a mu v mu phi equals a with lower index more times v with upper index mo.
Okay, that makes sense. If you contract an upper index and a lower index, they cancel out, leaving you with zero indices a scalar. And if phi is a scalar, we can plug this newly constructed product right back into our first axiom.
Exactly. We substitute the product in for phi. The equality partial nu, a mu v mu, the partial derivative with respect to x nu of the quantity a mu v mu equals nabla nu of the quantity a mu v mu.
Okay, let's focus exclusively on the right side of that equality for a moment. We are taking the covariant derivative, nabla, of a product of two variables. Just like in high school calculus, nabla must obey the product rule. The derivative of the first times the second plus the first times the derivative of the second.
Applying that rule yields the Leibniz product rule application nabla nu v mu plus a mu nabla nu of the quantity a mu v mu equals the quantity nabla nu of a mu times c mu plus a mu times the quantity nabla nu of v mu.
Let me stop you there. On the left side of our equality, the ordinary standard derivative of the product also follows the product rule. We expand that. And look at the right side. We have a term that is nabla of v with the upper index. We already know the formula for that. It's the one with the plus sign we literally just learned. So let's substitute all of those known pieces in to get one massive, fully expanded equation.
Expanding both sides gives us this. The full expansion v mu plus a mu, the partial derivative of a mu with respect to x nu times v mu, plus a mu times the partial derivative of v mu with respect to x nu, equals the quantity nabla nu of a mu times v mu, plus a mu times the quantity, partial derivative of v mu with respect to x nu, plus gamma mu nu sigma times v sigma.
I know that sounds like a wall of Greek to you listening, but if you look at this massive equation, a beautiful simplification immediately appears. On the left side, we have an a mu times the partial derivative of a v mu term. On the right side, if you distribute the a mu into the bracket, we generate that exact same term. We have identical terms on opposite sides of the equal sign. We can just cancel them out entirely.
That is correct. Subtracting that common term from both sides cleans the equation significantly, leaving us with the partial derivative of a mu with respect to x nu times v mu equals nabla nu of a mu times v mu, plus a mu times gamma mu nu sigma times v sigma.
Now, our ultimate goal is to isolate the unknown piece nabla nu of a mu. But before we just move things around with algebra, the text performs a very subtle critical index trick on that final gamma term to make the factoring clean. I want to spend some real time on this. Explain the dummy index swap.
The dummy index swap a mu gamma mu dis gamma v mu times gamma with upper mu and lower nu sigma times v sigma equals a sigma times gamma with upper sigma and lower nu mu times v mu.
I have to play devil's advocate here. You just changed a mu to a sigma and a sigma to a mu. You can't just arbitrarily swap letters in algebra. That changes the equation, doesn't it?
It does not, because of the rules of tensor summation. In tensor calculus, an index that appears once up and once down in the exact same term is called a dummy index. It implies a summation over all the dimensions of your space. Because it is merely a placeholder for a summation loop-like, the letter I or J in a computer programming, loop changing its letter, doesn't change the mathematical value of a sum at all as long as you swap them consistently within that single isolated term.
Okay, so it's like saying the sum of x from 1 to 3 is the exact same number as the sum of y from 1 to 3. The letter is irrelevant.
Exactly. We strategically swap mu and sigma so that every single term in our main overarching equation now shares a common factor v with an upper index mu.
That is brilliant foresight. So we pull that v mu out of everything, factoring it out. And because this equation must mathematically hold true for any arbitrary vector v mu we choose, the terms inside the parentheses must equal each other. We isolate nabla, move the gamma term to the other side of the equal sign, and what do we get?
The final covariant vector formula, nabla nu amu, a sigma nabla nu of amu equals the partial derivative of amu with respect to x nu minus gamma with upper index sigma and lower indices nu mu times a sigma.
The minus sign. We made it. It naturally falls out of the algebra. I want to really celebrate this moment because it is the core of the deep dive. Why did the math absolutely force a minus sign to appear for the covariant vector? I don't just want the algebra, I want the deep philosophical reason.
It is a profound demonstration of physical symmetry and balance. The fundamental axiom we started this entire proof with was that a scalar, a physical quantity independent of coordinates like temperature, cannot have any artificial correction terms when derived. It must be zero noise. But remember how we built our scalar. We built it out of a contravariant vector, which stretches with the coordinates, and a covariant vector, which shrinks inversely to the coordinates.
One stretches, one shrinks.
Exactly. Because the contravariant vector requires a positive Christoffel correction to cancel its coordinate noise, the covariant vector is mathematically mandated to have a negative Christoffel correction. The minus sign isn't an arbitrary choice made by a mathematician. It is the exact unyielding debt that must be paid to ensure the scalar remains perfectly unchanged. One twists right, the other twists left, and the minus sign is the fulcrum that balances them perfectly to zero.
That is incredibly satisfying. It's a masterclass in mathematical necessity. The universe demands equilibrium, and the minus sign provides it. Before we look at multiple indices, let's run a completeness check. I want to be absolutely certain we have rigorously proven the emergence of this minus sign via the Leibniz rule. Are there any conceptual gaps?
The proof is airtight. The logic flows unbroken from the axiom of the scalar to the necessity of the minus sign. We are conceptually secure and ready for method 2.
Which brings us to section 5.2. Method 2. Expanding to a 0-2 tensor. This directly answers the very first question of our mission today. Why do some tensors have two Christoffel terms? The text proves why a tensor with two lower indices gets two minus sign terms. Let's see how they set up this proof.
We use a similar trick to the one we just used. We pretend the tensor is made of simpler parts. The tensor product T mu nu equals A mu tensor product B nu.
So we treat this complex two-index tensor as if it were simply born from multiplying two single-index covariant vectors together. And because it's fundamentally a product, we rely on our trusty product rule again, right?
Precisely. You apply the covariant derivative, nabla, to the product. By the Leibniz rule, the derivative strikes the first vector, A mu, while leaving the second alone. Then it strikes the second vector, B nu, while leaving the first alone. Since both vectors are covariant with lower indices, applying the rule we literally just proved means each individual derivative strike generates its own independent minus sign Christoffel correction.
One strike, one minus correction. The second strike, a second minus correction. And when you recombine all of this back into the unified T-tensor notation, you get the final sprawling result.
The final two-index formula, nobler T mod sigma, gamma sigma, the gamma sigma, T mod T nobler rho of T mu nu equals the partial derivative of T mu nu with respect to X rho, minus gamma sigma rho mu times T sigma nu, minus gamma sigma rho nu times T mu sigma.
So two lower indices mathematically demand two minus terms. It stands to reason, if it were a massive tensor with three lower indices, there would be three minus terms, right? Each index is basically its own vector component that requires its own bespoke coordinate correction.
That is exactly right. Every index is a tether to the coordinate system, and every tether must be individually corrected for twisting.
Let's take a major step back and do a final core completeness check. We have just answered the overarching mission of this deep dive. We proved the minus sign and we proved in multiple terms. Do you feel like we have conquered the algebraic heart of this text?
We have structurally and conceptually answered both central questions. The minus sign and the multiple terms are undeniably proven. We have scaled the summit. We are now ready to descend into practical application in Chapter 6.
Chapter 6, Generalization and Concrete Example. Section 6.1 introduces what the text calls the golden rule. This is essentially a memory trick to formalize all this heavy algebra we just waded through. Upper index adds, lower index subtracts.
It is an elegant, sweeping synthesis of everything we've done. For any arbitrary tensor, no matter how massively complex, the algorithm is simple. You take the ordinary partial derivative of the whole thing. Then you systematically correct every single index, one by one. For every upper contravariant index, you add a Christoffel term. For every lower covariant index, you subtract a Christoffel term. It is a symphony of indices, all balancing each other out to preserve the absolute geometric truth of the object.
A symphony of indices. I think that rule is clear. Let's move to something highly visual. Section 6.2, a concrete example. Let's ground all of this heavy algebra in a real physical shape that everyone listening can instantly picture. A two-dimensional sphere, a globe. The text walks through a physical calculation here. Let's set up the math for our sphere.
The spherical metric, d theta 2 plus sin theta d theta d squared equals d theta squared plus sine squared of theta times d phi squared. Using this metric, this specific dynamic ruler for a globe, the text calculates the relevant twisting noise, the Christoffel symbols. The calculated Christoffel symbols, gamma theta phi syntheticos theta gamma with upper theta and lower phi phi equals minus sine theta times cosine theta, and gamma phi theta gamma with upper phi and lower theta phi equals cotangent of theta.
Okay, we have the noise calculated. Now, imagine we have a covariant vector field blowing across this sphere. Let's say it's a wind that blows steadily, perfectly uniformly along the lines of latitude, the phi direction. The vector's mathematical components are a theta equals 0 and a phi equals 1. Looking at those numbers, it looks perfectly constant. What happens when we take the covariant derivative along that latitude line, the phi direction?
The zero change derivative nabla phi a phi, all Viller 1, nabla phi of a phi equals 0. When you apply the full formula, all the Christoffel terms multiply by 0, and since the component is a constant 1, its partial derivative is 0. So moving east or west along the latitude line, the vector genuinely doesn't change.
But what if we check how this exact same vector changes as we move north or south along the theta direction towards the poles?
This is where the curvature reveals itself. The twisted derivative nabla theta a phi, nabla theta of a phi equals minus cotangent of theta.
Okay, I really want to emphasize this. If we just used ordinary calculus, the derivative of a constant number 1 is 0. Standard calculus says the vector isn't changing at all. But the rigorous covariant derivative says the answer is minus cotangent theta. What is the math actually telling us about reality on this sphere?
It is telling us that our numbers are deceiving us. If you only look at the raw coordinate numbers of the vector, 0 and 1, you think it is perfectly static. But visualize the grid of a globe. As you move away from the equator and travel up towards the North Pole, what happens to the lines of longitude, the lines of constant phi?
They bunch up, they converge until they pinch together at the pole.
Exactly. The physical geometry of the sphere is literally twisting and compressing the basis vectors as you move north. The covariant derivative, by outputting minus cotangent theta, is the mathematical proof that even if the vector's numerical components look constant on your spreadsheet, the space itself is twisting beneath the vector. The minus sign and the Christoffel symbol successfully captured the hidden curvature of the sphere that ordinary calculus completely ignored.
It caught the twisting stage. It proved that you can't trust the numbers without understanding the grid. Let's do a completeness check. Do you feel like this physical example sufficiently grounds the heavy algebra we did earlier?
Yes. Seeing the cotangent emerge as the physical manifestation of converging longitude lines makes the abstract math incredibly concrete. We are clear to move to the philosophical summary in Chapter 7.
Chapter 7, Philosophical and Geometric Summary. The text brings everything back to a deep physical intuition, introducing a concept called metric compatibility. This is fascinating. Let's see the equations before we unpack what it means.
Lowering the index, amu equals g mu times v nu, and the core philosophical axiom of the space. Metric compatibility nabla rho of g mu nu equals 0.
Okay, we must digress deeply into this idea of metric compatibility. The text says it means the physical act of parallel transport doesn't stretch or shrink your ruler. Walk us through this. What does this mean in the context of the journey we've been on today?
Remember that the metric tensor, g mu nu, is our dynamic ruler. It is the fundamental object that defines what length and angle mean at any given point in the universe.
Yeah.
Metric compatibility, stating that the covariant derivative of the metric tensor is exactly 0, is a profound physical demand we make of our universe.
A demand?
Yes. We are demanding that if I take a rigid physical ruler and I carry it with me as I walk along a wildly curved path through a warped space-time manifold, the ruler itself does not spontaneously change its own internal physical definition of length just because it was moved from point A to point B. The derivative, the change of the metric tensor must be absolutely 0.
So the ruler might tell me the space is warped, but the ruler itself isn't melting or stretching in my hands.
Exactly, because the metric tensor is the mathematical bridge that converts contravariant vectors, upper indices, into covariant vectors, lower indices, as seen in the first equation, and because the metric itself has 0 covariant change. The rules for differentiating those two types of vectors must be perfectly mirror-imaged to maintain this absolute stability. The minus sign is the literal reflection in that mirror.
Let me try to summarize this massive concept with the analogy from the text because it really crystallized it for me. The text compares the upper index to measuring distance and the lower index to measuring density. Let's say I'm measuring a running track. If I change my coordinate scale from meters to kilometers, a smaller, less frequent grid, the numerical value I use to describe that distance must increase to represent the same physical span. The measurement scales with the coordinates, requiring a positive correction. But what about density?
Let's follow the analogy. Density is mass per volume. If I change my scale from cubic meters to cubic kilometers, the denominator gets massive. The numeric value representing the density fundamentally shrinks. It transforms inversely.
Because there is less stuff packed into the new giant unit.
Right, because the metric tensor mathematically links distance and density, and because the metric our ruler cannot be allowed to change, the covariant derivative must automatically apply a negative correction to the density measurement to perfectly offset the positive correction applied to the distance measurement.
It all comes back to balance. If you pull one side of the equation, the other side must push back equally, or the ruler breaks. Completeness check. Are we certain we have extracted the philosophical core of metric compatibility?
The intuitive link between the metric, the stability of parallel transport, and the necessity of the minus sign is securely established. We are ready for the grand finale, the historical conclusion.
Chapter 8. The historical conclusion and final summary. The triumph of Einstein, covering the years 1912 to 1915. The text tells an incredible human story here. Einstein is in Zurich. He is visiting his old friend from university, the mathematician Marcel Grossmann. Einstein has a breathtaking physical intuition for gravity, the equivalence principle, the idea that mass actually bends the stage of space-time, but he is desperate. He is hitting a wall. He does not have the math to describe his vision. What happens in Zurich?
Grossmann hands Einstein the keys to the universe. Grossmann was a geometer. He went to the library, looked at Einstein's problem, and realized that the math Einstein needed had already been invented. He points Einstein directly to the absolute differential calculus, the tensor calculus painstakingly built by Riemann, Christoffel, Ricci, and Levi Civita over the last 50 years. He hands Einstein the covariant derivative. Einstein takes these exact formulas, the ones we just derived today, complete with their balancing Christoffel symbols and their absolutely crucial minus signs, and he uses them to formulate the ultimate theory of gravity. Let's look at the pinnacle of that achievement. The Einstein field equations, rho mu nu minus 1/2 r times g mu nu equals kappa times t mu nu.
This is where we emphasize the ultimate real-world stakes of our deep dive. What happens if Christoffel didn't figure out that noise term? What happens if Levi Civita didn't rigorously prove the necessity of that minus sign? What if they got the algebra wrong?
If that minus sign is wrong, Einstein's equations completely collapse. Look at the left side of that equation, the Ricci tensor, r mu nu. It represents the curvature of space-time. It is built entirely, 100%, out of complex combinations of covariant derivatives and Christoffel symbols. Without the rigorous proof of the minus sign, the left side of Einstein's equation, the geometry of the universe, cannot balance with the right side, which represents the mass and energy of the universe.
The stage wouldn't match the actors.
Without this specific math, we have no general relativity. We have no mathematical understanding of black holes. We cannot model the expansion of the cosmos. And on a purely practical, everyday level, the GPS satellites orbiting our planet right now, which require precise relativistic corrections to synchronize their clocks with the twisted space-time near Earth, would fail utterly. Your phone wouldn't know where you are. The modern world and our understanding of the cosmos literally balances on that single minus sign.
That is awe-inspiring. A century of obscure, abstract mathematics culminating in the ability to describe the shape of the cosmos and power the phone in my pocket. Okay, we have reached the end of the text. I want to pause and reflect on our journey for a final completeness check. We've executed our linear progression. We didn't skip the hard math. We deconstructed the history, the algebra, and the philosophy. Have we successfully extracted the secrets of the covariant derivative?
We have analyzed the history, rigorously derived the mathematics, maintained our pronunciation methodology, and connected the abstract algebra to physical reality. The text has been thoroughly unpacked.
Then I officially conclude the unabridged protocol for this deep dive. To you, the learner, thank you. Thank you for enduring and conquering such immense mathematical granularity with us today. This wasn't easy, it required patience. But I hope you see why this level of depth matters. The seemingly arbitrary rules of math, like a random minus sign popping out of a massive derivation, are not just academic torture. They are the universe's ultimate system of checks and balances. They are the hidden, unbreakable architecture of reality.
Before we part, I want to leave you with one final provocative thought, extending slightly beyond the boundaries of today's text. We relied entirely on the axiom of metric compatibility today. Nabla rho of gamma nu equals 0. We vehemently demanded that the ruler never changes length when you move it through space. But in theoretical physics, we must always question our axioms. What if we live in a universe where the ruler did change? What if parallel transport twisted not just the direction of an arrow, but its physical scale? I encourage you to look into something called whale geometry, or theories involving space-time torsion. These are alternative, highly advanced theories of gravity where the universe actually allows the covariant derivative of the metric to be non-zero. The math explodes in complexity, and it opens up entirely new, mind-bending possibilities for understanding the cosmos.
Space-time torsion. A twisting, stretching ruler. That is a perfect rabbit hole for you to explore next. Thank you for joining us on this incredible deep dive. Keep questioning the axioms and keep exploring the architecture of the universe. We'll see you next time. So, imagine you are an ant, but not just any ant. You're a two-dimensional ant living your entire life strictly on the surface of a giant sphere.
Okay, I'm picturing it.
You can walk forward, backward, left, and right, but you have absolutely no concept of up or down. You can't, jump off the surface to look at the shape of your world from the outside.
Because to you, the entire universe is just the ground you're walking on.
Exactly. So if you wanted to figure out if your universe was flat or curved, how would you do it?
It's a really profound question. And it perfectly sets the stage for what we are doing today. You're getting right to the heart of intrinsic geometry. I mean, how do you measure a curve when you can't step outside of it?
Right. And that thought experiment is the absolute foundation for today's deep dive. We are tackling an incredibly ambitious manuscript. It's 29,000 characters long.
It is massive.
The title is The Secret of the Covariant Derivative of a Tensor, and its minus sign, a 29,000-word full commentary through history, math, and philosophy. And I know what you, the listener, might be thinking, a whole deep dive about a single mathematical minus sign.
It sounds absurd on the surface, but this isn't just a quirk of algebra. The text argues, and we are going to explore exactly how, that this tiny, seemingly insignificant minus sign is the mathematical key that unlocked Albert Einstein's theory of general relativity.
That is the hook that makes this so fascinating to me. Without this specific minus sign, our modern understanding of gravity completely falls apart, right?
Completely. The existence of black holes, the expansion of the universe, even the fact that the GPS in your phone works, all of it, relies entirely on this minus sign. Our mission today is to deconstruct this manuscript. And we have to follow the unabridged protocol.
Which means we aren't skipping anything.
Nothing. We are going line by line, equation by equation, through the history, the math, and the philosophy. We have infinite time to unpack the why behind every single concept. We're focusing on the anatomy of the math. What do these equations actually mean for the fabric of reality?
If we just read equations like a textbook, it's impossible to follow. We need to ground this in physical reality. The text explicitly tells us that to solve this mystery, to answer the dual questions of why a minus sign and why are there two terms in the equation, we have to think like a 19th century mathematician trying to measure that ant's spherical universe.
Before we move on to the history, let's do our first completeness check. Does this and analogy fully set up the core mystery of the title? Have we missed any nuances in the intro?
I think we've thoroughly unpacked the core premise and the stakes. The listener knows exactly what we are hunting for.
Perfect. Then I confirm we are clear to transition into Chapter 1 of the manuscript.
Let's do it. Chapter 1 is titled Historical Background Differentiation on a Surface. Section 1.1 takes us all the way back to the 17th century, to Gottfried Wilhelm Leibniz and Isaac Newton.
The heavyweights who invented calculus.
Right. And the text points out that when calculus was born, it was essentially a tool for finding a slope or a rate of change. But, and this is a massive bull, but it was designed for flat paper, Euclidean space.
Yes, and on a flat piece of paper, finding a slope is beautifully simple. Flat space is perfectly consistent. If you draw a grid, the lines stay perfectly straight and parallel forever. But the manuscript forces us to ask a crucial why question here.
Why did mathematicians eventually feel the need to move past flat paper?
Exactly. Why start agonizing over curved surfaces like spheres or saddle shapes?
Well, because reality isn't flat. I mean, it's the most basic observational truth. The Earth is a sphere, the universe has curvature.
Right.
If calculus, the ultimate mathematics of change, only works on perfectly flat paper, then it fundamentally cannot describe the real world. That seems like a massive existential crisis for early mathematics.
It was a centuries-long bottleneck. Mathematics had evolved to describe perfect imaginary spaces, but it broke down when confronted with the bumpy, curved reality of nature. Time for a completeness check on section 1.1. Is the crisis of flat space calculus clear?
Flat math is officially broken when it comes to the real world. I'd say the premise is locked in. Let's move to section 1.2, jumping ahead to the year 1827.
Enter Carl Friedrich Gauss.
Yes, with his monumental work, the Theorema Egregium, which translates to the remarkable theorem.
This is where your ant analogy becomes mathematically rigorous. Gauss is the architect of intrinsic geometry. He proved, mathematically, that a two-dimensional creature living strictly on a surface can measure its curvature entirely from the inside.
Oh, wait, let me stop you there and ask why. If the ant has no concept of 3D space, how does measuring a local angle or distance tell it anything about the global shape of the planet it's standing on?
It sounds impossible, but Gauss figured out the workaround. Think about drawing a triangle. On a flat piece of paper, the angles of a triangle always add up to exactly 180 degrees. Always.
Basic geometry, yeah.
But if the ant draws a massive triangle on the surface of the Earth, say, starting at the North Pole, drawing a line straight down to the equator, moving exactly 90 degrees along the equator, and drawing a line straight back up to the North Pole, the angles will add up to way more than 180 degrees.
Because the surface itself is bulging outward, distorting the lines.
Exactly. Gauss proved that by taking incredibly precise local measurements of distances and angles, you can mathematically deduce the global curvature without ever leaving the surface.
That is genuinely brilliant. You don't need a God's eye view. The geometry of the curve is baked into the surface itself. But the text points out that while Gauss made this massive leap, he still lacked a generalized tool for what we call vector differentiation on these surfaces.
Right, he proved curvature could be measured intrinsically, but the everyday mathematical toolkit for tracking moving objects on those curved surfaces just wasn't there yet. Completeness check. Do we have Gauss and his remarkable theorem fully unpacked?
We do. Gauss opened the door to intrinsic geometry, so let's look at who walked through it in section 1.3. We are at the year 1854 with Bernhard Riemann.
Riemann is an absolute legend. The text highlights his famous Göttingen lecture on Riemannian manifolds. He essentially took Gauss's ideas, which were mostly about 2D surfaces, and blew them up to work in any number of dimensions.
And more importantly for our deep dive, he introduced a foundational concept, the ruler.
Yes, the ruler concept is where the math starts to get intensely physical. Riemann declared that in a curved space, the tool you use to measure distance, your literal ruler, might physically change depending on exactly where you are and what direction you are pointing in.
To formalize this, the manuscript introduces our first major piece of mathematics. We need to follow the pronunciation protocol exactly.
I'm ready.
The metric tensor, metric GAG subscript mu.
Perfect. Now let's look at the anatomy of that expression. It's just a lowercase g with two little subscript Greek letters, mu and no. But conceptually, what is it?
The text describes it as a matrix of numbers that acts as the ultimate local ruler. It tells you exactly how to calculate distance at one specific coordinate point.
Exactly, it's a dynamic measuring stick. But as the text reveals, introducing this dynamic ruler created a terrifying new crisis in physics.
Because of the implications for universal laws, right?
Yes, think about it. If your ruler changes depending on where you stand, and your coordinate grid lines are constantly twisting and changing density, how do you write a universal law of physics?
You can't. A fundamental law of physics like the conservation of momentum shouldn't change just because I moved from a flat Cartesian grid in New York to a curved polar coordinate grid in London. The physics must remain invariant.
Precisely. The physics must not care about the grid. Riemann provided the architectural blueprint for curved space, but in doing so, he shattered our ability to confidently take a derivative. If everything is relative to the twisting local geometry, finding an absolute rate of change seems impossible.
Completeness check time. Has Riemann's metric tensor and the resulting coordinate crisis been fully unpacked?
It has. Riemann built the landscape, but it's completely unnavigable, which perfectly sets up section 1.4, the year 1869, and Elwin Bruno Christoffel.
If this manuscript is a movie, Christoffel's the guy who hacks the mainframe. He realized that if your changing coordinates are messing up your calculus, you need to invent a mathematical mechanism to explicitly offset those changes.
He engineered a correction term, a localized shock absorber for calculus. The text introduces his legendary discovery. Let's get the math on the board.
The Christoffel symbol, or affine connection, capital gamma superscript, lambda subscript mu.
Let's break down the anatomy. It's a big Greek gamma. It has one index on top, lambda, and two on the bottom, mu and nu. The text emphasizes that Christoffel used this symbol to define the covariant derivative.
Which is what, exactly?
It's a way of taking a derivative that mathematically glides along with the coordinates. As the coordinates twist and distort, the Christoffel symbol actively counteracts the distortion. It ensures the physical meaning of your measurement remains perfectly unchanged, or invariant.
So it filters out the noise of the coordinate system so you can see the pure physical reality.
That's exactly it. Time for a completeness check. Has we sufficiently introduced Christoffel, his symbol, and the concept of the covariant derivative?
Yes, the shock absorber is officially installed. Now for the final piece of the historical puzzle in section 1.5. We're at the year 1900 with Gregorio Ricci Carbastro and Tullio Levi Civita.
The manuscript explains that they took Christoffel's raw mathematical symbol and weaponized it into an entire system called absolute differential calculus. Today we just call it tensor calculus.
What was their main contribution?
Systematization. They established a core, unshakable principle for the new century of physics. If a physical quantity is a true tensor, meaning it represents absolute physical reality, then its derivative must also be a tensor.
Meaning it must remain invariant no matter how radically you warp, stretch, or bend the coordinate system. You cannot take the derivative of a real physical object and have the result devolve into mathematical garbage just because your grid lines are curved.
Exactly. The integrity of the physics must survive the math. Let's do a completeness check on Chapter 1. We just covered roughly 230 years of history, from Leibniz's flat paper to Levi Civita's tensor calculus. Does that close out the historical context?
It thoroughly covers the historical evolution. We are now ready to transition into body, Section 3, Chapter 2 of the manuscript, where we build the basic conceptual tools.
Chapter 2 is titled Building Basic Concepts. Before we can solve the mystery of the minus sign, the text insists we have to rigorously define what we are actually taking the derivative of. Section 2.1 introduces the Great Divide.
Contravariant vectors versus covariant vectors.
This distinction is the engine driving the entire manuscript. We have to take our time here. Let us begin with contravariant vectors. The text associates these with physical quantities like position or velocity.
And the defining characteristic of a contravariant vector is how it scales when you change your coordinate system. The text says it scales with the coordinates.
Yes. The manuscript gives a specific example here. Let's say you zoom out on your coordinate system so that the numbers representing your grid double. The components of your contravariant vector will also double so that the physical vector arrow keeps pointing the exact same spot in space. Let's get the math format for this.
The contravariant vector manual mu masked rho v superscript mu.
And the text gives us the strict transformation rule for how it behaves when the grid changes.
The transformation rule manual mu mathrel oxomatral 8 bro b prime superscript mu equals the partial derivative of x prime superscript mu with respect to x superscript nu times v superscript nu.
Let's really analyze the anatomy of that equation because it looks intimidating.
It does.
The term on the left, v prime superscript mu, is our vector in the new zoomed-out coordinate system. The term on the far right, v superscript nu, is our vector in the old coordinate system.
And that fraction in the middle, the partial derivative, is simply the scaling factor. It's the mathematical bridge converting the old grid to the new grid.
Crucially, notice that the new coordinates, the x primes, are in the numerator of that fraction. Because the new coordinates are on top, the vector components scale proportionately with the new grid.
Okay, that makes sense. But then we have the mirror image, covariant vectors. The text asks us to think of quantities like gradients or the steepness of a slope. These do the exact opposite. They scale inversely to the coordinates.
Let's think about the physics of a slope to understand why. If you stretch your coordinate grid out so that the distance between points doubles, the physical steepness of the slope is now spread over twice the distance.
Therefore, the numerical value representing that steepness must have. It's scaled inversely. Let's state the mathematical representation for this type of vector.
The covariant vector of the subscript mu.
Notice the crucial difference in notation here. The index mu is now a subscript at the bottom rather than a superscript at the top.
That upper versus lower placement is going to be the key to everything, and its transformation rule is flipped upside down compared to the contravariant one. Let's read it.
The transformation rule master anu. A prime subscript mu equals the partial derivative of x superscript nu with respect to x prime superscript mu times a subscript nu.
Look at the anatomical difference in the scaling fraction here. For the covariant vector, the old coordinates x superscript nu are in the numerator. The new coordinates x prime superscript nu are in the denominator.
That mathematical flip is what guarantees the inverse scaling behavior. This fundamental behavioral difference between upper indices and lower indices is the seed from which our mysterious minus sign will eventually grow.
Let's pause for a completeness check. Have we fully established the difference between contravariant and covariant vectors?
One scales proportionately, the other scales inversely. The notation and the scaling rules are crystal clear. Let's move to section 2.2, which asks a deceptively simple question. What is a tensor?
The manuscript is incredibly strict about this definition. It warns us not to fall into the trap of thinking a tensor is just a spreadsheet of numbers or a simple matrix.
Right, you can't just scribble 9 numbers in a square grid and declare, behold, a tensor. The text defines a tensor by its behavior.
It is a physical quantity that transforms under those rigorous, unbroken scaling rules we just discussed, regardless of how wildly you change the coordinate system.
It must represent an absolute physical reality that all observers, no matter how their local grids are warped, can mathematically agree upon.
To ground this, the text provides 2 specific archetypes. First, a tensor with one contravariant component an upper index and one covariant component a lower index.
Well, the one tensor tic nu superscript mu subscript nu.
Second, a tensor built entirely of 2 covariant components.
The tensor dice of t subscript mu nu.
And the text explicitly reminds us that our dynamic ruler from earlier, the metric tensor g subscript mu nu, is the ultimate example of a zero tensor. Both of its indices are lower, meaning its components transform entirely inversely to the coordinates.
So a tensor is essentially a stubborn physical truth that refuses to be altered by the arbitrary grid lines we draw over it. Does that wrap up the foundational tools in Chapter 2? Completeness check.
It does. The concepts of covariance, contravariance, and the strict definition of a tensor are firmly in place. We are now prepared to witness the mathematical catastrophe in Body Section 4, Chapter 3.
Chapter 3 is dramatically titled The Crisis of the Ordinary Derivative. This is where we see exactly why standard flat paper calculus fails the reality test. Section 3.1 sets up a brilliant visual using a transition from flat space to polar coordinates.
The manuscript asks you to visualize standard flat Cartesian space. You have an x-axis and a y-axis. The Betis vectors, the little arrows defining what forward and up mean, are absolute constants. They point the exact same way whether you are at the origin or a million miles away.
Let's state the equation for a position vector in this comfortable flat space.
Position vector in Cartesian math BFU are x math BFER plus y math BFER. Vector r equals x times vector I plus y times vector j.
Those I and j vectors are your solid, unchanging foundation. But the text says, let's look at the exact same flat space, but measure it using polar coordinates using radius and angle instead of x and y. Think of a radar screen.
Position vector in polar media r, vector r equals r times the unit vector e hat subscript r's.
And here's where the illusion of stability breaks. Look at the anatomy of that polar basis vector, e hat subscript r. It always points directly outward from the center.
But imagine walking in a perfect circle around the center origin. As you walk, your physical location changes, which means the direction of outward is continuously rotating.
That's a great visual. Even though the piece of paper you are walking on is perfectly flat, the mathematical arrows defining your local grid are spinning around like a compass needle near a magnet.
And if the very arrows defining your reality are twisting as you move, and you try to calculate a rate of change using a standard ordinary derivative, it's going to accidentally measure the spinning of the grid and confuse it with the actual movement of the object.
Completeness check. Has that crisis of the twisting basis vectors been clearly laid out?
The geometric intuition of the crisis is perfectly clear. Now, the manuscript demands we prove this failure mathematically in Section 3.2. This is the rigorous proof of the failure of the ordinary derivative.
The text says, let's try to take an ordinary derivative of a contravariant vector and watch it break.
The ordinary derivative immanence partial nu v mu, the partial derivative subscript nu of v superscript mu.
To prove it breaks, we have to show that this resulting derivative does not behave like a true tensor. It won't transform cleanly. Let's walk through the anatomy of this proof. First, we imagine shifting our coordinates, and the text uses the chain rule from basic calculus to start the transition.
The chain rule step, phi rule step, frac partial v real, frac partial v of a, frac partial x alpha. The partial derivative of v prime superscript mu with respect to x prime superscript nu equals the partial derivative with respect to x prime superscript nu of the quantity. The partial derivative of x prime superscript mu with respect to x superscript alpha times v superscript alpha.
Okay, let's take a breath and look at what is trapped inside those massive parentheses. We have a product. It's the old vector v superscript alpha being multiplied by the scaling fraction.
Because we are taking the derivative of two things multiplied together, the rigorous laws of calculus dictate we must apply the product rule. The derivative of the first times the second plus the first times the derivative of the second.
Let's read the exact application of that rule.
The product rule application makes frac partial x alpha, makes alpha partial x alpha plus v alpha x nu equals the partial derivative of x prime superscript nu with respect to x prescript alpha times the partial derivative of v superscript nu with respect to x prime superscript nu plus v superscript alpha times the partial derivative with respect to x prime superscript nu of the partial derivative of x prime superscript nu with respect to x superscript alpha.
Let's pause and synthesize what just happened. The product rule essentially split our math into two separate halves. The first half actually looks okay. It's just the clean transformation of the derivative.
But we have to evaluate that second half. We apply the chain rule one last time to clean up the variables in that second half, and we get the final expanded equation.
The final expansion, partial x beta plus v alpha partial x beta plus v alpha first x most x beta equals the partial derivative of x prime superscript mu with respect to x superscript alpha times the partial derivative of x superscript beta with respect to x prime superscript nu times the partial derivative of v superscript alpha plus v superscript alpha times the second partial derivative of x prime superscript nu with respect to x prime superscript nu and x superscript alpha.
This equation right here is the smoking gun of the entire crisis. The text explicitly mandates that we deeply analyze that final term.
The one with the second partial derivative?
Yes, if the ordinary derivative were a true absolute tensor, only the first half of that equation would exist. But because we used the product rule on a twisting coordinate system, it spawned a parasitic mutant addition. The original vector multiplied by a massive second partial derivative.
The manuscript literally calls this second derivative term noise. It is mathematical garbage. It doesn't represent any physical reality. It is purely an artifact generated because our grid lines are curving.
So Christoffel and Riemann were completely right. When you use standard calculus on a curved surface, you aren't just measuring the velocity of the car, you're accidentally adding in the curvature of the road, and the math becomes useless.
Completeness check time. Does this algebraic proof of failure and the concept of noise fully satisfy our check for Chapter 3?
The derivation is complete, and the nature of the coordinate noise is fully exposed. The ordinary derivative is officially broken. We can now move to Body Section 5, Chapter 4, to engineer a solution.
Chapter 4 introduces the savior, Christoffel symbols. Section 4.1 dives into exactly how Christoffel designed this symbol. We know the ordinary derivative creates positive noise, so how do you get rid of it? The text explains Christoffel's reverse engineering logic.
It's an incredibly elegant piece of mathematical engineering. Christoffel essentially invented mathematical noise-canceling headphones.
I love that analogy. If you know how those work, they have a microphone that listens to the ambient static in the room. Then, the headphones artificially generate the exact inverse sound wave.
And when the positive static hits the negative artificial wave, they annihilate each other, leaving perfect silence.
Christoffel did exactly that, but with algebra. He saw the highly specific positive noise generated by that second derivative we just looked at, and he handcrafted a new symbol whose sole purpose in the universe is to generate the exact opposite negative noise.
Let's look at the terrifying transformation rule he designed for his symbol to achieve this cancellation.
The transformation rule, gamma lambda, froc partial, gamma lectamun, froc partial x mu, froc partial x mu, gamma sigma partial to gamma sigma brac partial left. Gamma prime superscript lambda subscript mu nu equals the partial derivative of x prime superscript lambda with respect to x superscript sigma times the partial derivative of x superscript rho with respect to x prim superscript rho tau minus the second partial derivative of x prim superscript lambda with respect to x superscript mu and x superscript nu times the inverse of the partial derivative of x superscript rho with respect to x superscript mu mu.
While the manuscript acknowledges that reading that equation is like chewing on gravel, it highlights the single structural masterstroke you must notice, the minus sign embedded right in the middle of it.
That minus sign attached to the second partial derivative is the active inverse wave in our noise-canceling headphones. It is genetically engineered to seek out and destroy the positive noise created by the ordinary derivative.
Completeness check. Has the design philosophy and the structural minus sign of the Christoffel symbol been adequately explained?
It has. The noise-canceling logic is brilliant. Now let's watch it work in section 4.2, where we finally construct the true covariant derivative of a contravariant vector.
The covariant derivative, partial nu v mu plus gamma nu nu subscript nu of v superscript nu, equals the partial derivative subscript nu of v superscript nu plus gamma superscript mu subscript nu sigma times v superscript sigma.
Notice the anatomy of this final pure equation. We replace the broken ordinary partial derivative, the partial symbol, with the new powerful covariant derivative operator represented by the inverted triangle called nubla.
And the equation dictates that the covariant derivative is equal to the ordinary derivative plus the Christoffel correction term.
But wait, the text gives us a strict y mandate here. Why are we adding them with a plus sign? We just spent 10 minutes talking about inverse waves and minus signs.
The explanation is beautiful. The ordinary derivative inherently produces plus noise. But, as we just saw in its massive definition, the Christoffel symbol gamma inherently has minus noise secretly baked into its very core.
So when you add them together with a plus sign, you are adding the poison to the antidote. The positive noise from the derivative and the hidden negative noise from the gamma symbol annihilate each other flawlessly.
And what remains is a perfectly clean, invariant mathematical object. By adding the gamma term, we have filtered out all the twisting, spinning, and stretching of the coordinate system, leaving us with a pure 1-1 tensor that perfectly describes the absolute physical rate of change.
That is deeply satisfying. Completeness check. Have we successfully differentiated a contravariant vector and explained the plus sign?
We have. The contravariant vector is solved. But that leads us directly to the precipice of our entire deep dive. Body Section 6, Chapter 5. This is the core mystery we set out to solve.
Chapter 5 is titled The Secret of the Minus Sign. Up until now, we've only fixed vectors with upper indices. Now we transition to covariant vectors, the ones with lower indices, like gradients and densities.
The central mystery of the manuscript is, why does differentiating a lower index covariant vector require an explicit minus sign in the formula, rather than the plus sign we just used?
Section 5.1 attacks this using Method 1, Intuitive Understanding via the Leibniz Rule. This proof is a masterclass in logical deduction. The text says, let's not guess. Let's start with something we already understand perfectly. A scalar.
A scalar is just a single number with no direction. Think of the temperature in a room. It might be 72 degrees. That number doesn't care if you measure the room using an XY grid or polar coordinates. The physical heat is invariant.
Because scalars ignore coordinates entirely, they produce absolutely zero coordinate noise. Therefore, taking a covariant derivative of a scalar is exactly the same as taking a standard ordinary derivative. Let's anchor that mathematically.
The scalar derivative partial mu phi nobilis subscript mu of phi equals the partial derivative subscript mu of c.
That is our unshakable foundation. Next, the manuscript instructs us to artificially construct a scalar by combining two vectors. If we take our covariant vector a subscript mu and take the inner product with our contravariant vector v superscript mu, the geometry dictates that the result is a pure scalar, which we will call phi.
The scalar inner product a mu v phi equals a subscript mu times v superscript mu.
Okay, so phi is a scalar, which means it is immune to noise. The text leverages this by stating that the ordinary derivative of this product must be perfectly equal to the covariant derivative of this product. Let's set up that equality.
Equating the derivatives of mu's nobile nu, the partial derivative subscript nu of the quantity subscript mu times v superscript mu equals nobilis subscript nu of the quantity a subscript v superscript mu.
Now the heavy algebraic lifting begins. The covariant derivative operator, nabla, obeys the product rule, also known as the Leibniz rule. The text demands we distribute the nabla across the vector product on the right side of our equation.
The derivative of the first times the second plus the first times the derivative of the second. Let's read the expanded form.
Distributing the nabla Leibniz rule nabla nublas al mu nabla subscript nu of the quantity a subscript mu times v superscript mu equals the quantity nabla subscript nu of a subscript mu times v superscript mu plus a subscript mu times the quantity nabla subscript nu of v superscript mu.
And we have to mirror that exact same distribution on the left side using the standard partial derivative.
Distributing the partial derivative partial nu amu plus amu partial derivative subscript nu of the quantity a subscript mu times v superscript mu equals the quantity partial derivative subscript nu of a subscript mu times v superscript mu plus a subscript mu times the quantity partial derivative subscript nu of v superscript mu.
We are building towards a synthesis. We substitute these expanded forms back into our central equality. Furthermore, remember Chapter 4. We already proved the formula for the covariant derivative of the contravariant vector v superscript mu.
Right, it was the ordinary derivative plus the Christoffel symbol.
Exactly. We must substitute that known formula into the right side of our massive equation. Let's read the full synthesis.
The synthesis equation moblana v mu partial nu amu plus amo nu amu plus sigma. The quantity partial derivative subscript nu of a subscript mu times v superscript mu plus a subscript mu times the quantity partial derivative subscript nu of v superscript mu equals the quantity nabla subscript nu of a subscript mu times v superscript mu plus a subscript mu times partial derivative subscript nu of v superscript mu plus gamma superscript mu subscript nu sigma times v superscript sigma.
If you look closely at the anatomy of that massive synthesis equation, something beautiful happens. On the far left, we have the term a subscript mu times the partial derivative subscript nu of v superscript mu.
And if you distribute the multiplication on the right side, you'll see the exact same term sitting there. Because they are perfectly identical on opposite sides of the equal sign, the text tells us we can completely cancel them out. They just vanish. Let's look at the cleaner equation that's left behind.
Canceling common terms, v k-o v sigma, the quantity partial derivative subscript nu of a subscript mu times v superscript mu equals the quantity nabla subscript nu of a subscript mu times v superscript mu plus a subscript mu times gomo subscript nu sigma times v superscript sigma.
We are inches away from the finish line. The manuscript notes a tiny bookkeeping issue on the far right term. Both mu and sigma are what mathematicians call dummy indices. They're essentially just blank placeholders indicating that a summation is happening.
To make factoring easier in the next step, the text instructs us to simply swap the label mu with the label sigma. It changes absolutely nothing about the underlying math.
Swapping dummy indices, a sigma gamma will a subscript mu times gamma superscript mu subscript nu sigma, cancel sigma subscript nu mu times v superscript mu.
Okay, after swapping those labels, look structurally at the entire equation again. Every single one of the three terms left is being multiplied by the vector v superscript mu. It is a universal common factor.
Because this equation must remain true for literally any arbitrary vector v we could possibly choose, we can simply factor it out and drop it from the entire equation.
Factoring out the v term, mycelium partial nu amu plus gamma sigma nu, the partial derivative subscript nu of a subscript mu equals nabla subscript mu of a subscript mu plus gamma superscript sigma subscript nu times a subscript sigma.
And here's the breakthrough. We want to isolate the covariant derivative of our lower index vector, nabla subscript nu of a subscript mu. To get it by itself, we simply take the gamma term and subtract it over to the other side.
The final breakthrough. A sigma nabla subscript nu of a subscript mu equals the partial derivative subscript nu of a subscript mu minus gamma superscript sigma subscript nu mu times a subscript sigma.
Boom! There it is. The minus sign. We finally found it. The text makes it perfectly, unequivocally clear. This minus sign is not some random convention that Christoffel decided upon. It mathematically must exist to preserve the balance of the universe.
Precisely. Remember, creating a scalar requires multiplying a contravariant vector and a covariant vector. The contravariant vector inherently brings positive noise into the product rule.
Therefore, if the final scalar is to remain perfectly pristine and noise-free, the covariant vector's derivative must inherently bring negative noise into the equation. The minus sign is the necessary cosmic counterweight, ensuring that when the two vectors combine, their respective noises annihilate each other to exactly zero.
Let's do a completeness check. Has the Leibniz rule proof and the existential necessity of the minus sign been fully unpacked?
The logic is airtight. The minus sign is the absolute counterweight to the plus sign. Now we have to tackle the second half of the mystery in section 5.2. Why two terms? The text extends this newly discovered minus sign logic to a 0-2 tensor.
To understand this, the text says we can imagine our 0-2 tensor t subscript mu nu as being artificially constructed by gluing together two separate covariant vectors, which we'll call a and b.
The tensor product, smizis t mu nu o times b nu, equals a subscript mu tensor product b subscript nu.
So it's a composite object made of two lower indices. Once again, because it's a product, we apply the foundational product rule to find its covariant derivative.
Applying the product rule, nabla benu, nabla subscript rho of t subscript mu nu equals the quantity nabla subscript rho of a subscript mu times b subscript nu plus a subscript mu times the quantity nabla subscript rho of b subscript nu.
Now the substitution is easy. We literally just proved that the derivative of covariant vector A requires a minus sign Christoffel correction, and the derivative of covariant vector B requires a minus sign Christoffel correction. We substitute those formulas in.
Substituting the minus sign formulas minus arrow, partial hero minus hour, minus sigma plus amu bema sigma equals the quantity partial derivative subscript rho of a subscript mu minus gamma superscript sigma subscript rho mu times b subscript nu plus a subscript mu times the quantity partial derivative subscript rho of b subscript nu minus gamma superscript sigma subscript rho nu times b subscript sigma.
By distributing the a and b vectors back through the parentheses, and remembering that a tensor product b equals our original tensor t, the manuscript reveals the final monumental formula for a 0-2 tensor.
The final zero nabla subscript rho of t subscript mu nu equals the partial derivative subscript rho of t subscript mu nu minus gamma superscript sigma subscript rho mu times t subscript sigma nu minus gamma superscript sigma subscript rho nu not size t subscript mu sigma.
And there's the answer to why two terms. The anatomy of the math mirrors the anatomy of the physical object. The tensor has two lower indices, mu and nu.
Because each individual index is tied to a changing coordinate basis, each index acts as an independent source of geometric noise.
Therefore, you need two independent minus sign Christoffel corrections acting as bodyguards, one to stabilize and silence the noise of the mu index, and one to stabilize the nu index.
Time for a massive completeness check. Have the dual mysteries of the minus sign and the multiple correction terms been entirely resolved?
We have successfully solved the title mystery. The algebraic proofs are complete. Let's see how this all synthesizes in Body Section 7, Chapter 6, Generalized Formula and Example.
Chapter 6 moves us from pure theory to pragmatic application. Section 6.1 distills all of our agonizing proofs into a single mnemonic, the golden rule.
It's incredibly simple now that we've done the hard work. Add for upper indices, subtract for lower indices.
If you have a massive tensor with 5 upper indices and 3 lower indices, you know exactly what to do. You write out the ordinary derivative, then you add 5 positive Christoffel terms and subtract 3 negative Christoffel terms. It's an infallible recipe for noise cancellation.
It guarantees geometric stability. Completeness check. Have we captured the essence of the golden rule?
The rule is set. Now the manuscript challenges us with Section 6.2, an extensive mathematical example, calculating a vector derivative on a 2D unit sphere. We are finally putting the ant back on the sphere to do some real calculations.
Let's set up the geometry. We are on a perfect sphere with a radius of 1. We're using spherical coordinates, measuring position by the angles theta for latitude and phi for longitude. First, we need the metric, the absolute ruler for the surface of a sphere.
The spherical metric metastonalor is definido major that meter isotype plus sin theta d Sjosted equals d theta squared plus sine squared theta d phi squared.
From that distance equation, the text extracts the metric tensor matrix, which is the actual mathematical ruler we will use to navigate.
The metric tensor begin matrix 1 in matrix and end P4 and sin theta and matrix and matrix theta and Pietro Venu with rows 1, 0, and squared theta.
We also need the inverse of that matrix, which simply involves flipping the diagonal elements.
The inverse metric matrix and a P-par and sin factory matrix save the matrix G superscript mu nu with rows 1, 0, and 0, 1 over sine and squared theta.
Now we need our noise-canceling headphones. We have to calculate the Christoffel symbols for this specific sphere. The text provides the general formula, which is a beastly combination of partial derivatives of our metric tensor.
The Christoffel calculation formula, gamma lambda mu nu, partial nu nu sigma, cashel muju sigma, partial nu sigma, partial nu tashel mu nu, gamma superscript lambda subscript mu nu equals 1/2 g superscript lambda sigma times the quantity partial derivative subscript mu of g subscript nu sigma plus partial derivative subscript nu sigma minus partial derivative subscript sigma of g subscript mu nu.
The manuscript does the heavy lifting of crunching the sine and cosine derivatives through that formula, and it highlights 2 specific non-zero results that will affect our ant's journey. Let's state them.
Calculating the first gamma theta, gamma superscript theta subscript phi equals negative sine theta cosine theta.
Calculating the second, gamma superscript theta subscript theta phi equals cotangent theta.
With the corrections calculated, the text gives us a very specific covariant vector to analyze.
Setting the covariant vector mu, a subscript mu equals 0, 1.
So the theta component is 0, and the phi component is a constant 1. It's a vector pointing purely along the lines of longitude. First, the text calculates the covariant derivative of this vector as you move in the phi direction.
Derivative along phi nebulovi eva. Nebuli vela subscript phi of a subscript phi equals 0.
Okay, that makes intuitive sense. Moving along longitude doesn't twist this specific vector, but then the text calculates the covariant derivative as you move in the theta direction, moving down the lines of latitude.
Derivative along theta a phi, enable a subscript theta of a subscript phi equals negative cotangent theta.
Wait. We need to stop and deeply analyze this result. The component we are differentiating, a subscript phi, is exactly the number 1. It is a constant. If I am in high school calculus, the derivative of a constant is always 0, period. But this covariant derivative just spit out negative cotangent theta. Why isn't it 0?
This is the triumphant physical payoff of the entire manuscript. The math is revealing a hidden geometric truth. Even though the number describing the vector component is a constant 1, the actual physical arrow representing that vector on the surface of the sphere is physically twisting and changing direction because the curved surface of the sphere is bending underneath it as you walk south in the theta direction.
So the ordinary derivative is essentially blind. It looks at the number 1, shrugs, and says, nope, no change here. But the covariant derivative, armed with those Christoffel symbols, can actually feel the curvature of reality. It detects that the vector is twisting through space and outputs the exact mathematical description of that twist, negative cotangent theta.
Let's do a completeness check. Does this fully unpack the sphere example and its physical implications?
It beautifully demonstrates the superiority of tensor calculus over flat math. The physical reality of the twisting vector is undeniable. This naturally transitions us into Body Section 8, Chapter 7, where the manuscript synthesizes the philosophy and geometry of everything we've done.
Chapter 7 aims to tie all this rigorous 19th century algebra back to deep physical intuition. Section 7.1 asks us to look at the deep relationship between contravariant and covariant vectors. The text explains that they aren't two completely isolated species of math. You can fluidly transform one into the other using our absolute ruler, the metric tensor.
Lowering the index trencher and anew. A subscript mu equals G subscript mu nu times V superscript nu.
To understand the profound implications of this transformation, the manuscript dictates that we take the covariant derivative of that exact relationship.
Differentiating the relation of nu nabla subscript rho of A subscript mu equals nabla subscript rho of the quantity G subscript mu nu times V superscript nu.
In doing this, the text introduces what it calls the most vital, foundational physical requirement of our universe, the metric compatibility axiom.
Metric compatibility axiom nabla subscript rho of G subscript mu nu equals 0.
Okay, let's unpack the why behind this axiom. Why must the derivative of the metric tensor equal exactly 0? The text explains metric compatibility with a very grounded physical analogy.
It means that if you take a solid physical object, like a wooden ruler, and you slide it perfectly parallel along a highly curved surface, the ruler itself does not spontaneously stretch or shrink. The distance it measures remains absolute.
It's the assumption of physical rigidity. If this axiom wasn't true, physics as we know it would be impossible. Imagine building a spacecraft on Earth where gravity curves space a certain way and then flying it to Jupiter where the curvature is massive.
If your physical measuring sticks mathematically expanded or contracted just by moving through curved space, the ship would tear itself apart. Setting the covariant derivative of the metric tensor to exactly 0 mathematically enforces the reality that rulers maintain their length.
The manuscript then uses another brilliant physical analogy to summarize why upper indices and lower indices behave so differently and why the minus sign preserves reality. Let's compare measuring distance to measuring density.
Think of a contravariant vector with an upper index, like measuring the distance between two cities. If you switch your map's coordinate grid from meters to kilometers, meaning your base unit gets much larger, the numerical value you use to describe the distance must increase to continue pointing at the exact same physical city. You scale with the change.
Conversely, think of a covariant vector with a lower index, like measuring mass density kilograms per cubic meter. If you expand your coordinate grid, making the theoretical cubic meter box much larger, the numerical value representing the density must decrease to accurately describe the exact same physical concentration of mass. The scaling is inverse.
The minus sign we spent Chapter 5 deriving is not a mathematical punishment. It is the vital mechanism that preserves the physical reality of that denominator. It ensures that when space expands, the calculation of density correctly scales down.
Time for a completeness check. Have the philosophical connections, the metric compatibility axiom, and the unit scaling analogies been fully explored?
They have. The philosophy makes the algebra feel inevitable. The math works the way it does because reality works the way it does. Which brings us to the grand finale, Body Section 9, Chapter 8. The historical conclusion, Einstein's triumph.
The manuscript brings all of this abstract, purely theoretical 19th century mathematics crashing into the 20th century. The setting is the year 1912. Albert Einstein is in a state of deep intellectual frustration.
Right. Einstein already published special relativity, but gravity is driving him mad. He has this incredible physical intuition that gravity isn't a magical pulling force, but rather the actual curving of space and time itself. Heavy objects dent the mattress of the universe.
But he is stuck because he doesn't have the math to prove it. Every time he tries to write an equation for twisting space, it generates useless mathematical garbage. He is drowning in coordinate noise. So he turns to his friend, the mathematician Marcel Grossmann.
Grossmann realized exactly what Einstein needed. He reached into the mathematical archives and handed Einstein the work of Ricci and Levi Civita. He handed him absolute tensor calculus. He handed him the metric tensor, the Christoffel symbols, and the covariant derivative.
He handed him the noise-canceling headphones. Armed with Christoffel's meticulous, minus sign-wielding math, Einstein finally cut through the coordinate noise. He was able to formulate his masterpiece. Let's look at the anatomy of arguably the most important equation in the history of physics.
Einstein field equations R subscript mu nu minus 1/2, R times G subscript mu nu equals kappa times 2 subscript mu nu.
Look at the left side of that equation. The r subscript mu nu is the Ricci curvature tensor. The manuscript emphasizes with absolute certainty that this curvature tensor is constructed almost entirely out of covariant derivatives. This is the grand why of the entire deep dive.
Without Christophel's agonizing discovery of the minus sign correction for covariant derivatives, Einstein could never have mathematically stabilized the curvature of spacetime.
That one tiny minus sign in the middle of a 19th century algebraic proof is the linchpin of reality. Because of it, we can calculate the expansion of the universe. We can understand the mechanics of black holes.
And on a purely practical level, the GPS array connecting to your smartphone right now has to run general relativity calculations to sync its clocks with Earth because gravity curves time. If it didn't use Christophel's minus sign, your GPS would be off by miles within a single day.
The mathematics of the abstract became the engineering of the everyday. Let us perform a final recap of the ultimate equation that made this entire journey possible.
Final recap of the ultimate equation, machnablo unbonunu. Take serio, quiere brace. Nabo by underbrace gamma sigma. Demo sigma t gamma, underbrace gamma sigma wunu. Demo sigma hon textimo t monu text demo subscript munu minus the first lower index correction gamma superscript sigma subscript ronu times t subscript sigma nu minus the second lower index correction gamma superscript sigma subscript ronu times t subscript mu sigma.
The ultimate expression of balance. Two lower indices, two sources of noise, two perfect minus sign corrections to silence them. Does that complete our analysis of Chapter 8 and the triumph of Einstein?
The historical conclusion and the physical implications of the mathematics have been exhaustively verified. We have successfully completed the structural outline of the entire 29,000-character manuscript.
To you, the listener. We started by asking you to imagine an ant on a sphere. Over the course of this deep dive, you didn't just learn a neat trivia fact. You walked the exact, rigorous intellectual path carved out by Gauss, Riemann, Christoffel, and Einstein over 2 centuries.
You didn't just memorize a formula, you deconstructed the very logic of how space bends. If you look at those equations now, they aren't just a nightmare of Greek letters. You know exactly what they are doing. You understand the noise of changing coordinates, and you understand the elegant noise-canceling symmetry engineered to silence it.
It is a remarkable journey of human thought. But before we sign off, we must leave you with a final provocative thought that extends beyond the boundaries of the text we just analyzed. Throughout this exploration, we relied heavily on that metric compatibility axiom, the mathematical law stating that nabla subscript rho of g subscript mu nu equals 0.
This is the assumption that a physical ruler does not stretch or shrink when moved across curved space.
But physicists never stop questioning assumptions. I invite you to ponder. What if we lived in a universe where the rules were fundamentally different? What if the fabric of space exhibited a property called torsion or non-metricity?
That is a wild thought. What if, as you moved your wooden ruler from Earth to Mars, the actual intrinsic structure of the vacuum caused the ruler to stretch entirely independently of gravity?
If metric compatibility was broken, the beautiful, perfectly balanced, noise-canceling symmetry of the Christoffel symbols we just spent an hour deriving would shatter. The math of reality would require entirely new, infinitely more complex asymmetric correction terms to track how objects warp as they move.
It opens the door to incredibly exotic alternative theories of gravity. I highly encourage you to go down that rabbit hole on your own, imagining a universe where the measuring stick itself is alive and constantly changing.
It is a profound frontier of modern theoretical physics.
Yeah.
As for our task today, I will perform one final summation. The entirety of the manuscript has been deconstructed, the mathematics have been grounded in physical reality, and the mystery of the minus sign has been solved.
Absolutely. Thank you for sticking with us through the dense math and the deep philosophy. It's an intensely rigorous topic, but deeply rewarding when you finally see how the mathematical fabric of our universe is woven together. Catch you on the next deep dive.
Welcome. I want you to get comfortable, remove all distractions, and just prepare your mind. Today, you and I are embarking on an intensely granular, highly specialized deep dive into the very fabric of reality.
We really are.
We aren't just skimming the surface of a topic. We are taking a microscopic lens to the architecture of the universe itself. We're going to be unpacking a dense, brilliantly detailed, a 29,000 character masterclass. It's titled The Secret of the Covariant Derivative of a Tensor and its Minus Sign.
Right.
Now, I know what you might be thinking. A whole deep dive dedicated to a single mathematical minus sign.
Yes.
Absolutely. Because our mission today is to deconstruct exactly why a minus sign appears in one of the most fundamentally important equations in all of physics.
It really is the anchor of modern physics.
Exactly. This isn't just some abstract mathematical quirk or a typo on a chalkboard. This specific minus sign, nestled inside this specific type of derivative, is the mathematical load-bearing pillar that makes Einstein's general relativity work. It's the reason we can understand black hole physics, the reason we can model the expanding universe. And on a very practical level, it is the exact reason the GPS system on your phone can accurately pinpoint your location as you drive down the street. Without this minus sign, our entire understanding of gravity and space-time literally collapses into nonsense.
That is precisely the scale of the stakes we are dealing with today, and it's wonderful to be here diving into this with you, because when you look closely at the history of physics, it's often these tiny, seemingly innocuous details, a single flipped sign, a subtle change in a geometric rule that unlock the greatest mysteries of the cosmos. And to do this justice, we're going to strictly adhere to what we call the unabridged protocol.
Right, we should explain that.
Yes. The unabridged protocol means we are going to operate under the assumption that we have infinite time. We will process the source material strictly in order from start to finish. We won't skip a single sentence, concept, or formula. We will proceed line by line, and after every single concept, we will perform a rigorous completeness check to ensure absolutely no stone is left unturned.
That covers the intro and the mission statement, as well as the unabridged protocol. Have we missed any nuances before we begin the actual text?
I think we've thoroughly unpacked it. Let's proceed to the opening preamble and the core mystery.
Okay, let's unpack this. The source material makes a bold, almost audacious thesis right up front. It states that the covariant derivative, and specifically the fact that it uses a minus sign when dealing with a certain type of vector, is the absolute essence of general relativity and differential geometry.
And to truly understand why, we have to strip away all our everyday common sense intuition about how space works. We are so used to living in a flat, three-dimensional world where lines are straight and grids are perfect. But the universe doesn't actually work like that.
Right. And to help us break out of that flat world bias, the text gives us a fantastic analogy right out of the gate. I want you to imagine the perspective of an ant. A tiny ant crawling on the surface of a perfectly smooth apple. If you are that ant and you're just walking straight forward, placing one foot in front of the other, you might genuinely believe you are moving in a perfect, flat, straight line.
Because your immediate surroundings look flat to you.
Exactly. But to us, an observer looking at the ant from a higher three-dimensional perspective, we can clearly see that the ant is tracing a curved path along the skin of the apple. The core mystery we are trying to solve today is this. How do you, the ant, calculate the change in your direction, or the laws of physics happening around you, without ever being able to leave the surface of that apple to look at it from the outside?
And that analogy gets right to the heart of the why. Why are we obsessing over a minus sign? Because if that ant is trying to write down the fundamental laws of physics, say the laws of momentum or fluid dynamics or gravity, those laws cannot depend on some imaginary external 3D grid that we impose from the outside.
The ant doesn't have access to that grid.
Precisely. The laws must be mathematically intrinsic. They have to be written entirely in the language of the apple's surface. The minus sign in the covariant derivative is the mathematical mechanism that perfectly accounts for the twisting, turning, and bending of the underlying space itself. It acts as a filter. It separates the true physical change of a moving object from the fake change that is caused merely by the fact that the space itself is bending beneath the object. If we get that single sign wrong, the ant's physical laws break down. The universe's geometry becomes mathematically inconsistent.
That covers the preamble, the ant analogy, and the fundamental why of our deep dive.
Yeah.
Have we missed any nuances here?
I think we've thoroughly unpacked it. Let's proceed to Chapter 1 and the historical quest for the derivative.
Moving to Section 1.1. Humanity didn't just wake up one day and invent this math. It was a centuries-long struggle. The text takes us all the way back to the 1600s, to the very birth of calculus with Gottfried Wilhelm Leibniz and Isaac Newton. When they first birthed the concept of the derivative, it was beautifully simple. It just meant slope or rate of change. If I'm driving a car, my derivative is my speed, how my position changes over time. But the text highlights a crucial, fatal limitation of their early calculus. Leibniz and Newton were entirely operating on flat paper. They built their math for a Euclidean space.
Exactly. Euclidean space is the geometry you learned in high school. Straight lines are perfectly straight, parallel lines never intersect, and the grid of x and y axes extends infinitely in all directions without ever warping or stretching. Leibniz and Newton gave us a magnificent tool to measure change, but it was a tool built strictly for a perfectly rigid, flat stage.
In a flat Euclidean space, your measuring sticks never change their length, and your compass never changes its angle no matter where you move them.
Right. And mathematicians immediately recognized a primary conflict. How do you measure a slope or a rate of change if you were living on a sphere or a hyperbolic saddle? If the paper itself is bent, how does the original flat paper derivative survive? It doesn't. And that was the great unsolved mystery that lingered for over a century. The moment you ask, what is the slope of a curve on a sphere? You run into a profound philosophical and mathematical wall.
That covers section 1.1, Leibniz, Newton, and the Euclidean limitation. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's
Yeah.
proceed to section 1.2 and Gauss.
This brings us to a massive paradigm shift. The text moves us forward to the year 1827 and introduces Carl Friedrich Gauss. He publishes a monumental paper called General Investigations of Curved Surfaces. And Gauss completely flips the script with what he calls the Theorema Egregium, the remarkable theorem. This is where our ant analogy really takes flight.
What's fascinating here is the sheer elegance of Gauss's proof. Before Gauss, to measure how much a sphere was curved, mathematicians thought you had to step outside the sphere into a 3D space and measure its radius from the center. Gauss proved that a 2D creature, our ant living strictly on the surface, could just draw triangles, measure their internal angles, and determine the curvature of their universe entirely from within.
Right, because on a flat piece of paper, the angles of a triangle always add up to exactly 180 degrees. Always.
Precisely. But if our ant draws a massive triangle on the surface of the Earth, say, starting at the North Pole, going down to the equator, moving a quarter of the way around the equator, and then going straight back up to the North Pole, that triangle has three 90-degree angles. It adds up to 270 degrees.
It's blowing the ant's mind.
Oh, completely. The ant measures that 270 degrees and knows with absolute mathematical certainty that it lives on a positively curved surface. It never has to look up into a third dimension to know this. This brilliant realization birthed the entire field of intrinsic geometry.
But as the text notes, while Gauss conquered intrinsic curvature for static shapes, he still hit a wall. He figured out how to measure the landscape, but he lacked the general vector derivative tools to describe how moving quantities, like fluid flows or shifting magnetic fields, changed as they moved across these intrinsic landscapes. He laid the foundation, but the house wasn't fully built yet. That covers section 1.2 and Gauss's Theorema Egregium. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 1.3 in Riemann's revolution.
It's 1854, and Bernhard Riemann, Gauss's own student, delivers a revolutionary lecture at the University of Göttingen. He completely shatters the limitations of 2D surfaces and introduces Riemannian manifolds, which are basically curved spaces of any number of dimensions. You want a four-dimensional warped universe. Riemann gives you the math for it.
And here is where he introduces a concept that is truly mind-bending. He declares that the ruler we use to measure distance can change at every single point in space. Which brings us to our first mathematical protocol block. The metric tensor is metric tensor, G sub mu nu.
That covers the introduction of the metric tensor. Have we missed any nuances on the formula itself?
I think we've thoroughly unpacked the notation. Let's explain why it functions as a changing ruler.
Let's do that. Imagine a flat map of the Earth, like a standard Mercator projection map you'd see on a classroom wall. If you take a plastic ruler and measure a centimeter near the equator on that map, it might represent 100 physical miles. But if you take that exact same plastic ruler and measure a centimeter way up near Greenland, it suddenly represents only 10 physical miles.
Exactly. The paper map is flat, but the meaning of distance on that map changes wildly depending on your coordinates because the map is trying to represent a curved sphere. Riemann formalized that exact concept. The metric tensor is essentially a continuously shifting conversion rate for your coordinates. It adapts point by point.
But this brilliant realization brings the overarching problem of our source text into sharp, terrifying focus. As Riemann showed, in a curved space, the coordinate grid is constantly warping, squeezing, and stretching, and the metric tensor ruler is constantly shifting to keep up. So how on earth do you write down a law of physics, a derivative that measures true objective change, when the very coordinate grid you are using to measure it is morphing beneath your feet? That covers section 1.3, Riemann and the changing ruler. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 1.4, the historical solution.
This coordinate morphing crisis required a hero. In 1869, a German mathematician named Erwin Bruno Christoffel steps onto the stage. The text frames him as the hero of this mathematical saga, and rightfully so. He discovered a special correction term designed specifically to offset the complex, chaotic changes that occur when you shift coordinate systems in a curved space.
Which brings us to our next mathematical protocol block. The Christoffel symbol, or affine connection, is gamma lambda gamma super lambda sub mu nu.
That covers the definition of the Christoffel symbol. Have we missed any nuances?
I think we've thoroughly unpacked the notation. Let's explain the physical why behind it.
Please. Why is this symbol so absolutely crucial?
To understand the Christoffel symbol, we have to rethink what taking a derivative actually means. When you take a derivative, you are comparing a vector like an arrow representing wind speed at one point to a vector at a slightly different point nearby. But in Riemann's curved spaces, you can't just slide an arrow over and compare it to its neighbor. Why? Because the coordinate axes themselves have rotated and stretched during that tiny slide. If you just subtract the raw numbers, you get garbage.
So Christoffel's genius was realizing that you need a mathematical bookkeeper.
Exactly. The Christoffel symbol is the ultimate geometric bookkeeper. It precisely calculates exactly how much the coordinate grid itself twists and stretches as you move from point A to point B. By factoring in this correction term, you can calculate the fake coordinate-induced twisting and subtract it out. What you are left with is only the true, objective physical change of the vector. This brilliant maneuver gave birth to what we now call the covariant derivative.
That covers section 1.4 and Christoffel's bookkeeping symbol. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 1.5 and the completion of the historical quest.
In 1900, Italian mathematicians Gregorio Ricci-Curbastro and his brilliant student Tullio Levi-Civita take Christoffel's isolated ideas and forge them into a comprehensive, indestructible framework known as tensor calculus.
And they establish a golden, non-negotiable rule for physics. If a physical quantity is a real, measurable thing, a true physical entity, which they called a tensor, then its derivative must remain a tensor invariant under coordinate transformations.
Meaning, physics must be democratic. It shouldn't matter if you are using a rectangular grid, a polar grid of circles and angles, a spherical grid, or an arbitrarily squiggly grid drawn on a rubber sheet. The fundamental physical change must translate perfectly across all of them without breaking. By systematically utilizing Christoffel's bookkeeping symbols, Ricci and Levi-Civita created an absolute differential calculus. They solved the 200-year-old mystery of how to do calculus on a curved surface. That covers section 1.5 and the birth of tensor calculus. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to chapter 2, sharpening the tools.
Here is where it gets really interesting, because we need to look under the hood. The text tells us that vectors, those mathematical arrows we use to describe the world, are actually split into two deeply distinct types: contravariant vectors and covariant vectors.
The names are archaic and confusing, but the underlying concepts are surprisingly intuitive. It's all about how these vectors react when you mess with the coordinate grid. Let's start with the first type, contravariant vectors.
Time for the math protocol blocks. The contravariant vector is Vmo v supermu.
That covers the contravariant vector definition. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's move to its transformation rule. The coordinate transformation rule for contravariant vectors is Fach partial x fractly v prime supermu equals the partial derivative of x prime supermu with respect to x supernu times v supernu.
That covers the contravariant transformation rule. Have we missed any nuances?
I think we've unpacked the formula. Let's explain what it physically means. The text gives us a beautiful analogy. A contravariant vector represents things like position, velocity, or a physical distance. It scales with the coordinates. The superscript is mathematically treated like a numerator in a fraction.
Right. Think about zooming in on a digital map. Imagine you are tracking a car moving at a certain speed. If you suddenly shrink your coordinate units, say, moving from measuring distance in kilometers to measuring it in meters, your grid units just got 1,000 times smaller. Therefore, the numerical value of your velocity vector has to scale up proportionally to cover the same physical ground. A velocity of 1 kilometer per second becomes 1,000 meters per second.
The components contravary. They adjust in tight coordination with the grid to ensure that the physical arrow points to the exact same physical spot in space. If the grid shrinks, the number gets bigger to compensate.
Exactly. Superscripts scale up when the grid scales down. Now let's contrast this with the second type.
Right, the covariant vectors. The covariant vector is a mu a sub mu.
That covers the covariant vector definition. Have we missed any nuances?
I think we've unpacked it. Let's do the transformation rule. The coordinate transformation rule for covariant vectors is on mu brumpeltom a's on nu prime sub mu equals the partial derivative of x super nu with respect to x prime super mu times a sub nu.
That covers the covariant transformation rule. Have we missed any nuances?
I think we've unpacked the formula. Let's dive into the physical meaning. In the math, these are written with a subscript, an index placed down low. And here, the subscript acts like a denominator in a fraction.
Yes, the text tells us covariant vectors represent entirely different physical concepts, things like gradients, fields, or the normal force pushing off a surface. They scale inversely to the coordinates.
How does a gradient act like a denominator?
Imagine a gradient as a measure of steepness on a topographic map. How much elevation you gain per unit of horizontal distance. If you change your map's grid from measuring in tiny meters to measuring in massive kilometers, your unit step across the map is suddenly much, much larger. Therefore, the total elevation change you experience over that massive new unit step is going to be a huge number. But the steepness itself hasn't changed at all.
Alternatively, if your grid units get incredibly small, moving from kilometers to millimeters, the numerical value of the elevation gradient over that tiny new millimeter unit gets extremely small. It scales inversely to our distance example. It covers with the coordinate basis itself.
That distinction is massive. Superscripts scale like a physical distance arrow. Subscripts scale like a measurement of steepness or density. This fundamental difference in how they react to the grid shrinking or expanding is the absolute beating heart of why the minus sign will eventually appear. We are building the engine right now.
That covers section 2.1, the difference between contravariant and covariant vectors. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 2.2, assembling them into tensors.
The text insists that we must unlearn a common misconception here. A tensor is not just a fancy spreadsheet of numbers. It is not just a matrix you type into a computer. A tensor is a physical, geometric entity that strictly obeys those specific transformation rules we just discussed, regardless of how you rotate, stretch, or warp your perspective.
Let's look at the math blocks for this. The 1,1 tensor is 2 mono t super mu sub nu.
That covers the 1,1 tensor. Have we missed any nuances?
I think we've unpacked it. Let's do the next one. The 0,2 tensor is 2 mo t sub nu.
That covers the 0,2 tensor definition. Have we missed any nuances?
I think we've unpacked the notation. Let's break down the nomenclature. A1 tensor means the tensor is built with one superscript and one subscript. It transforms like a velocity vector in one dimension and like a steepness gradient in the other. A linear transformation matrix often acts like a 1,1 tensor.
And the 0,2 tensor has 0 superscripts and 2 subscripts. It transforms purely covariantly, twice over. The metric tensor we discussed earlier, the changing ruler of space, is a perfect example of a 0,2 tensor. It takes in 2 vectors and spits out a measurement of length or angle. What's vital for you to remember here is that those superscripts and subscripts are not just labels, they are the tensor's DNA.
Exactly. Every superscript demands a specific mathematical transformation rule where the new coordinates are in the numerator. Every subscript demands a specific transformation rule where the new coordinates are in the denominator. A tensor's true identity is defined entirely by how it reacts when the universe's coordinate grid is yanked out from under it. If it survives the yank according to the rules, it's a real tensor. If it breaks, it's just a matrix of numbers.
That covers section 2.2 on tensors. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to chapter 3, the crisis of the ordinary derivative.
The text asks a very pointed question. Why do we even need this complicated covariant derivative with all its Christoffel symbols? Why can't we just use the ordinary derivative we all learned in introductory calculus? To answer this, the text contrasts a flat Cartesian grid with a polar coordinate system.
In a flat Cartesian grid, your standard graph paper with x and y axes, the basis vectors, which are the little arrows that define one unit up and one unit right, are constant. They point in the exact same direction with the exact same length everywhere in the entire universe. Up is always up, right is always right.
But the moment you switch to a polar coordinate system, which maps space using a radius pointing outward and an angle sweeping in a circle, things go completely haywire. In polar coordinates, your basis vector for the radius always points outward, away from the center. If you are standing at the top of a circle, the radial vector points straight up. If you walk 90 degrees along the edge to the right side of the circle, the radial vector now points strictly to the right. The physical direction of the basis vectors changes wildly depending entirely on your position.
That covers section 3.1, flat versus polar grids. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 3.2 and the mathematical failure of the ordinary derivative.
If we try to take an ordinary derivative of a vector field in this polar environment, it completely breaks the golden rule of physics. The ordinary partial derivative is not a tensor. It fails to be a physical reality.
Let's bring in the math protocol to show this. The ordinary partial derivative of a vector field is partial nu v mu, the partial derivative with respect to v super mu.
That covers the definition of the ordinary partial derivative. Have we missed any nuances?
I think we've unpacked it. Now, the text walks us through an excruciatingly detailed proof using the chain rule and the product rule from calculus to show exactly what happens when we change coordinates. Step 1. The first step using the chain rule is for partial x partial v alpha, the partial derivative of v prime supermo with respect to x prime supermo equals the partial derivative with respect to x prime superno of the quantity. The partial derivative of x prime supermo with respect to x super alpha times v super alpha.
That covers step 1 of the proof. Have we missed any nuances?
I think we've unpacked it. Moving to step 2. Applying the product rule yields frac partial x alpha frac partial left of the alpha frac right. The partial derivative of x prime supermo with respect to x super alpha. The partial derivative of v super alpha with respect to x prime super nu plus v super alpha times the partial derivative with respect to x prime super nu of the partial derivative of x prime super mu with respect to x super alpha.
That covers step 2, applying the product rule. Have we missed any nuances?
I think we've unpacked it. Now the final expansion step. The final expanded form is frac partial x beta, partial x nu frac partial x beta partial phi partial x nu, the partial derivative of x prime super mo with respect to x super alpha times the partial derivative of x super beta with respect to x prime super mu times the partial derivative of v super alpha with respect to x super beta plus v super alpha times the second partial derivative of x prime super mu with respect to x prime super nu and x super alpha.
That covers the final expanded form of the proof. Have we missed any nuances?
I think we've unpacked the formulas. Now let's analyze the wreckage of that split.
Yes. If the ordinary derivative were a true tensor, it would transform beautifully. The first piece of the split we just read is exactly that, a clean, elegant scaling of the original derivative. It transforms perfectly. But because of the product rule acting on the changing coordinate grid itself, we are infected by the second piece, a massive, ugly second term.
That second term is the noise. And what is that noise mathematically? It is a second derivative. Specifically, the second derivative of the coordinates themselves. Physically, a second derivative represents acceleration. This means your derivative calculation, your attempt to measure how your wind speed is changing, is being violently contaminated by the acceleration or the curvature of the coordinate grid you happen to be using.
Right. If you change from a straight grid to a twisting, turning grid, this second term injects phantom changes into your math. It's exactly like sitting in a car that takes a hard left turn. You feel a force pushing you to the right. That centrifugal force isn't a real gravitational pull, it's a fictitious force, an illusion caused entirely by the fact that your frame of reference, the car, is accelerating.
The ordinary derivative suffers from mathematical centrifugal force. The golden rule of tensors, that they must transform purely and invariantly, is broken. The ordinary derivative is exposed as a coordinate illusion. That covers section 3.2 and the failure of the ordinary derivative. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to chapter 4, the savior, the Christoffel symbols.
A crisis demands a savior. Enter Christoffel and his brilliant reverse engineering. Christoffel didn't try to fix the ordinary derivative directly. He accepted its flaw. Instead, he designed his symbol to be a highly specific mathematical antidote. He engineered its transformation rules so that when you change coordinates, the Christoffel symbol violently ejects a second derivative term that is the precise negative mirror image of the noise generated by the ordinary derivative.
That covers section 4.1 and the definition of the antidote. Have we missed any nuances?
I think we've unpacked it. Let's see it in action in section 4.2. Time for the math protocol. The covariant derivative of a contravariant vector is nablanu, probably of vmo plus gamma mu nu sigma, that sub nu of v super mu equals the partial derivative with respect to nu of v super mu, plus capital gamma super mu sub nu sigma times v super sigma.
That covers the definition of the covariant derivative for a contravariant vector. Have we missed any nuances?
I think we've unpacked the formula. So what does this all mean conceptually?
We add the plus noise from the ordinary derivative to the minus noise from the Christoffel symbol, and they perfectly cancel out. It creates a perfect mathematical symphony of cancellation. When you shift your perspective, the ordinary derivative spits out its ugly noise related to the bending of the grid. But simultaneously, the Christoffel symbol spits out an identical negative noise. You add them together, and they perfectly, flawlessly obliterate each other.
The coordinate illusions vanish. What remains is a pure, untainted tensor. A physical law that is true regardless of the observer's perspective. The covariant derivative is the ultimate truth-teller in a warped universe. That covers section 4.2 and the cancellation of noise. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to Chapter 5, the core, the minus sign revealed.
We have arrived at the summit, the central mystery of the 29,000 character text. We just established that differentiating a contravariant vector, a superscript, requires adding the Christoffel symbol to cancel the noise. But the bold thesis at the very beginning stated that differentiating a covariant vector, a subscript, requires subtracting the Christoffel symbol. Why a minus sign? The text provides an epic logical proof to reveal exactly where this minus sign comes from, relying on something called the Leibniz rule.
This proof is a masterpiece because it uses a Trojan horse. It relies on something we deeply trust, something that the twisting coordinate grid cannot possibly affect, a scalar. A scalar is just a single number, like the temperature of a room. It has no direction. Because it has no direction, it doesn't care if the basis vectors of your grid are twisting or turning. It's immune to the geometry. Therefore, the ordinary derivative of a scalar works perfectly fine. It's already a perfect tensor.
Let's bring in the math protocol for this first piece. The covariant derivative of a scalar is a nabla phi nabla sub mu of phi equals the partial derivative with respect to mu to phi.
That covers the covariant derivative of a scalar. Have we missed any nuances?
I think we've unpacked it. Now, how do we use this immune scalar to prove the rule for our vulnerable vectors? We smash them together. We take a contravariant vector and multiply it by a covariant vector. This process is called a scalar contraction. It mathematically merges the two directional vectors and collapses them down into a single directionless scalar number. Let's do the math. The scalar contraction is E phi equals A sub mu times V super mu.
That covers the scalar contraction formula. Have we missed any nuances?
I think we've unpacked it. So we now have an equation, a perfect scalar on one side and the multiplied pair of vectors on the other. Because it's an equation, we apply an operation to both sides simultaneously to see what shakes loose. We apply our derivatives. The text gives us the formula. Applying the derivative to both sides gives partial nu, almosu, the partial derivative with respect to nu of the quantity A sub mu times V super mu equals nabla sub nu of the quantity A sub mu times V super mu.
That covers applying the derivative to both sides. Have we missed any nuances?
I think we've unpacked it. Now, because we are taking the derivative of a product of two vectors, we have to use the Leibniz rule, the product rule.
Yeah.
It's like a scale. The derivative operator acts on the first vector while leaving the second alone, and then acts on the second vector while leaving the first alone. We expand both sides out massively. Let's do the right side first. Expanding the right side using the Leibniz rule yields nabla amu plus amalu in the quantity nabla sub nu of A sub mu times V super mu plus A sub mu times the quantity nabla sub nu of V super mu.
That covers expanding the right side. Have we missed any nuances?
I think we've unpacked it. Now the left side. Expanding the left side yields R partial nu amu plus anu, the quantity partial derivative with respect to nu of A sub mu times V super mu, plus A sub mu times the quantity partial derivative with respect to nu of V super mu.
That covers extending the left side. Have we missed any nuances?
I think we've unpacked it. Now this is where the magic happens. We've expanded the equation into a sprawling mess. But we have a cheat code. We already know the formula for the covariant derivative of the contravariant vector. It's the ordinary derivative plus the Christoffel symbol. We substitute that definition right into the middle of our massive equation. Let's look at the result. Equating and expanding both sides results in partial nu mu plus a mu plus a mu, partial nu amu plus amu gamma mu nu sigma, the quantity partial derivative with respect to nu of A sub mu times V super mu, plus A sub mu times the quantity partial derivative with respect to nu of V super mu equals the quantity nabla sub nu of A sub mu times V super mu, plus A sub mu times the quantity partial derivative with respect to nu of V super mu, plus A sub mu times capital gamma super mu sub nu sigma times V super sigma.
That covers equating and expanding both sides. Have we missed any nuances?
I think we've unpacked it. Now, if you look closely at that resulting algebra, There is an identical term sitting on both the left side and the right side of the equals sign. In algebra, when you have the exact same weight on both sides of a balancing scale, you can just pull it off. We cancel out the common terms. Let's see what's left. Canceling the common term leaves delano v sigma plus amu gamma mu, the quantity partial derivative with respect to nu of a sub mu times v super mu equals the quantity nabla sub nu of a sub mu times v super mu plus a sub mu times capital gamma super mu sub nu sigma times v super sigma.
That covers canceling the common term. Have we missed any nuances?
I think we've unpacked it. Now we do a little bit of algebraic housekeeping, swapping some dummy indices to factor things out neatly. Swapping dummy indices gives mo gamma nu sigma as sigma gamma times capital gamma super mu sub nu sigma times v super sigma equals a sub sigma times capital gamma super sigma sub nu mu times v super mu.
That covers swapping the dummy indices. Have we missed any nuances?
I think we've unpacked it. And now the final blow. We isolate our target, the covariant derivative of the covariant vector. We want it alone on one side of the equal sign. To do that, we move the Christoffel symbol term from the right side over to the left side. And when a positive term crosses the equal sign, it becomes negative. Isolating the target term gives the final proof. Nabla nu amu gamma sigma, a sigma nabla sub nu of a sub mu equals the partial derivative with respect to nu of a sub mu minus capital gamma super sigma sub nu mu times a sub sigma.
That covers the final proof and the isolation of the target term. Have we missed any nuances?
I think we've thoroughly unpacked it. And boom, look at that, the minus sign. We didn't just guess it. We didn't just throw it in because it looks symmetrical or pretty. It was mathematically inevitable. It exists specifically and purely to cancel out the plus noise that is inherently generated by the contravariant vector during that scalar contraction we set up.
Because the final scalar must remain perfectly invariant and immune to the grid, the covariant vector is forced, by the iron laws of calculus, to transform with a minus sign to perfectly offset the contravariant vector's plus sign. It is a stunning, inescapable piece of mathematical clockwork.
That covers section 5.1, the proof of the minus sign using the Leibniz rule. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 5.2, extending this logic to 0-2 tensors.
Right. What if you have a true tensor, like a 0-2 tensor, which has two subscripts? Well, because it is made of two covariant pieces, the derivative must distribute its corrections to both indices independently. And because they are both subscripts, they both require the minus sign. Let's see the formula. The final formula for a 0-2 tensor is nabla whole kamala sub rho of t sub nu equals the partial derivative with respect to rho of t sub nu minus capital gamma super sigma sub rho mu times p sub sigma nu minus capital gamma super sigma sub rho nu minus capital gamma super sigma sub rho nu times t sub mu sigma.
That covers the formula for the 0-2 tensor. Have we missed any nuances?
I think we've unpacked it. Why two terms? Because if the grid is twisting, it's twisting the first dimension of the tensor and the second dimension of the tensor. They must both be accounted for, and they're both minus because they are both subscripts. That covers section 5.2. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to chapter 6, the golden rule, and a concrete example.
Having climbed this incredible mountain of abstract algebra, the text gives us a beautiful view from the top in the form of a golden rule. It's a simple mnemonic to remember the sprawling complexity we just navigated. If you want to take the covariant derivative of any tensor, no matter how monstrously large, first, take the ordinary partial derivative. Second, look at the superscripts. For every superscript, add a Christoffel symbol term. Third, look at the subscripts. For every subscript, subtract a Christoffel symbol term. Add for superscripts, subtract for subscripts.
It is elegant, brutal, and flawlessly consistent. That covers section 6.1, the golden rule. Have we missed any nuances?
I think we've thoroughly unpacked it. Now, the text refuses to leave us floating in the realm of pure abstraction. It drags us back down to reality with a concrete example in section 6.2. We're going back to Gauss's 2D creature. We are going to actually calculate a covariant derivative on a 2D unit sphere. Imagine a perfect globe. We use spherical coordinates, theta for latitude, moving pole to pole, and phi for longitude, moving around the equator. First, we need the metric tensor, the mathematical ruler for the globe. The text provides a specific equation for this metric line element. The metric line element is 2 plus sin pi 2 2se2 d phi squared equals d theta squared plus sine squared of theta times d phi squared.
That covers the metric line element. Have we missed any nuances?
I think we've unpacked it. With the metric tensor in hand, we have to calculate our bookkeepers, the Christoffel symbols. This is usually a horrifically tedious process involving a massive formula with a lot of partial derivatives of the metric itself. Here is that general formula. The Christoffel symbol calculation formula is gamma lambda sigma partial n sigma capital gamma super lambda sub nu equals 1/2 times g super lambda sigma times the quantity. The partial derivative with respect to mu of g sub nu sigma plus the partial derivative with respect to nu of g sub nu sigma minus the partial derivative with respect to sigma of g sub nu.
That covers the massive Christoffel calculation formula. Have we missed any nuances?
I think we've unpacked it. The text zeroes in on calculating how the longitude basis vectors change as you move along the latitude. As you move from the equator towards the North Pole, they run the math, plugging the metric values into that formula, and it spits out two results. Let's look at the first. The result for the theta phi phi component is gamma theta. Sin theta k theta, capital gamma super theta sub phi phi, equals negative sine of theta times cosine of theta.
That covers the theta phi phi component. Have we missed any nuances?
I think we've unpacked it. And the second result. The result for the phi theta phi component is gamma theta theta phi, capital gamma superphi theta phi equals cotangent of theta.
That covers the theta phi component. Have we missed any nuances?
I think we've unpacked it. Now for the grand finale. We imagine a vector field on this sphere, a covariant vector field with a constant numerical value of 1. Imagine a wind blowing perfectly, constantly along the equator. If you take the ordinary derivative of a constant 1, you get 0. You'd think there is no change. But we know better now. We must apply the golden rule. We calculate the covariant derivative. We take the partial derivative, which is 0, and because it's a covariant subscript, we subtract the Christoffel symbol we just calculated. Let's look at the final math. Calculating the covariant derivative in the theta direction. Nabla theta a phi. Nabla sub theta of a sub phi equals negative cotangent of theta.
That covers the final calculation of the covariant derivative. Have we missed any nuances?
I think we've unpacked the math. So let's break down the physical meaning of this because it's profound. The ordinary derivative was 0, but the covariant derivative is negative cotangent theta. Why isn't it 0?
Because even if the wind speed is numerically constant on paper, the physical sphere itself is curving out from underneath it. As you move from the equator towards the North Pole, the physical lines of longitude squeeze closer and closer together. The basis vectors pointing east are physically twisting inward towards the pole.
The vector field is geometrically twisting through space, even though its numbers look constant. The minus sign, combined with the cotangent, mathematically captures that exact invisible geometric twist perfectly. The math sees the curvature of the sphere that the 2D ant cannot see. It proves that the abstract minus sign manifests as a very real, measurable physical truth. That covers section 6.2 in the concrete sphere example. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to chapter 7, the philosophical meaning of the minus sign.
This leads us to the overarching philosophy driving all of this math. It all hinges on one supreme axiom of Riemannian geometry, metric compatibility. The text explains that if you have a ruler, the metric tensor, and you move that ruler through space, the ruler itself cannot change its own length. The act of measuring cannot distort the measuring stick. Here is the formal math for that. Metric compatibility is expressed as nablarho bro of g sub nu equals 0.
That covers the metric compatibility formula. Have we missed any nuances?
I think we've unpacked it. Let's bring back our scale analogy and make this deeply relatable. Superscripts scale up to keep pointing to the same absolute place in reality when you shrink your grid. Subscripts scale down to keep the exact same physical ratio over a smaller volume.
The covariant derivative's job is to ruthlessly enforce metric compatibility. It must ensure that objective reality doesn't stretch or shrink just because you drew a weird grid on it. The minus sign is the dedicated mechanism that preserves the inverse scaling of subscripts while simultaneously canceling the noise of the twisting coordinates. The minus sign preserves objective reality.
That covers chapter 7 and metric compatibility. We missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to chapter 8, the grand conclusion.
And so we arrive at the grand conclusion. The historical story here is almost poetic. It's 1912. Albert Einstein is in Zurich, meeting with his friend, the mathematician Marcel Grossmann. Einstein has this magnificent, earth-shattering physical intuition. Gravity is not a pull, like Newton thought. Gravity is the actual warping and curving of space-time itself by mass and energy. But Einstein is stuck. He lacks the mathematical language to describe a four-dimensional warping space-time where the coordinate grid is entirely dynamic.
He needs a way to write physical laws that are absolutely true regardless of how severely the space is warped by a star or a planet.
Grossmann, being a brilliant mathematician, knows exactly where to look. He points Einstein to the obscure papers written over a decade earlier by Ricci and Levi-Civita, the tensor calculus, and nestled right in the heart of that calculus was the brilliant, tedious work of Elwin Bruno Christoffel and the inescapable law of the minus sign for the covariant derivative of a 0-way-2 tensor. Einstein took these pure, abstract mathematical tools and used them to forge the greatest equation in human history. The Einstein field equations. Let's look at the math one last time. The Einstein field equations are frac 1 to mu nu minus 1/2 r times g sub mu nu equals kappa times t sub mu nu.
That covers the Einstein field equations. Have we missed any nuances?
I think we've unpacked it. Let's emphasize the stakes one last time, exactly as the text does. The core of Einstein's equation is the Ricci curvature tensor, that r sub mu nu. It is built entirely out of covariant derivatives and Christoffel symbols. If Christoffel, Ricci, and Levi-Civita had made a mistake, if they had missed that minus sign when taking the derivative of those subscript components, Einstein's equations would be fundamentally wrong. General relativity would fail. Our understanding of the cosmos would shatter.
Without the tedious, grinding discovery of that specific minus sign rule, there is no understanding of the expanding universe. There is no understanding of the crushing singularity of a black hole. And, to bring it back to your daily life, the GPS satellites orbiting the Earth, which have to constantly calculate the curvature of space-time caused by the Earth's mass to keep your maps accurate, would fail within minutes. The clocks on the satellites tick differently than the clocks on your phone because of warped space-time, and the math with the minus sign is what syncs them back up.
That covers the grand conclusion and the connection to Einstein. Have we missed any nuances from the source text?
I believe we have successfully executed the unabridged protocol. We have thoroughly unpacked every single line, concept, and mathematical formula in the text.
It's unbelievable. As we close this incredibly rigorous journey, I want to leave you with one final provocative thought. Think about the timeline we just walked through. Riemann and Christoffel developed the mathematics of extremely curved, multi-dimensional space in the mid-1800s. They developed the metric tensors, the affine connections, the plus and minus signs of covariant derivatives, entirely as an abstract intellectual exercise. It was pure, unadulterated math, completely untethered to physical reality. They were just playing with logic. It sat on a dusty shelf for 50 years. Then, Einstein comes along and realizes that the tangible universe we actually live in, the stars, the planets, the bending of starlight, and the gravity keeping your feet on the floor, actually operates on those exact, precise rules. It forces us to ask, does humanity invent mathematics purely in our minds as a fun game, or do we slowly discover the hidden, pre-existing source code of reality? Thank you for joining us in this exhaustive deep dive into the architecture of the universe. The next time your phone successfully navigates you to a new coffee shop, take a brief moment of silence. Because quietly, furiously, deep in the silicon, a little mathematical minus sign, first imagined by a German mathematician in 1869, is diligently canceling out the curvature of the Earth just for you.
Welcome to The Explainer, where we break down big ideas. Today, we are on the hunt for a secret hiding in plain sight, right inside one of the most important formulas in all of modern physics. And you know, it's just a tiny detail, but it's a detail that completely changed our understanding of the entire universe. So here it is. This is the equation for something called the covariant derivative. And our entire investigation today boils down to one simple question. Why is there a minus sign right there? I know, it might look like just a tiny, insignificant detail, right? But believe me, that one little symbol is the key. It's the key to describing everything from the force of gravity to the actual shape of space-time itself. So, to crack this case, we've got to investigate the scene of the crime. And that scene is curved space. Before we can really get to the bottom of why that minus sign is there, we have to ask an even more basic question. Why do we even need this fancy covariant derivative thing at all? I mean, what was so wrong with the good old derivatives we all learned about in high school? Well, here's where it all starts. The problem kicks in when we try to do something that sounds super simple, like finding the rate of change of a vector. And you can think of a vector as anything with a direction, like velocity or a force field. The trouble begins when you try to do that on a surface that isn't perfectly flat, like, for instance, the surface of the Earth. And this slide right here shows you the problem perfectly. On the left, you've got flat space. Everything's easy. Your grid lines are straight, your directions are constant, north is always north. But look at the right side, curved space. On a sphere, everything gets warped.
The grid stretches, and more importantly, your basis vectors, your local sense of direction, they change from point to point. The north you feel at the equator is pointed in a completely different direction in 3D space than the north you'd feel near the pole. And this is exactly where ordinary math just breaks down. It gives you the wrong answers.
So the real culprits here are these things called basis vectors. You can just think of them as your local compass directions, your personal north, east, whatever, right at the point you're standing. But because they're constantly twisting and turning as you move around in curved space, a normal derivative gets totally confused. It's like trying to measure a car's speed while you're standing on a spinning merry-go-round. The derivative can't tell, is the car actually moving, or is it just me that's spinning?
So what's really happening is that a standard derivative accidentally mushes two different things together. It measures the true change in the vector that we care about, but it also picks up all this coordinate noise from the grid itself changing underneath it. It's getting contaminated data. It's kind of like trying to weigh yourself on a scale that's inside a moving elevator. The number you see on the scale isn't your true weight, is it? It's your weight plus or minus the effect of the elevator's acceleration. Same idea here. So to fix this, mathematicians realized they needed a tool, basically a noise-canceling tool for math, something that was specifically designed to measure that coordinate noise perfectly, and then subtract it out, leaving behind only the pure, true change in the vector we were trying to measure in the first place. And this didn't just happen overnight. You can see from the timeline this was a slow burn. You had the absolute giant Carl Friedrich Gauss kicking things off way back in 1827. Then, Bernhard Riemann comes along and just blows the whole concept up into higher dimensions with manifolds. They were laying this incredible groundwork for decades, until finally, in 1869, a guy named Elvin Bruno Christoffel comes along and invents the perfect tool to solve the whole derivative problem. And he called it the Christoffel symbol. You can think of it as this little mathematical machine whose entire job, its only reason for being, is to capture that exact amount of noise we were just talking about. It precisely measures how the basis vectors are changing from one point to the next so that we can finally get rid of that contamination and find the truth. Okay, now here's where it gets really interesting. It turns out there are kind of two different flavors of vectors. For the first type, called a contravariant vector, and you can always spot these because they have their index written up top, the math shows that the coordinate noise actually comes out as a positive value. So to correct for it, to cancel it out, what do? You add a correction term with the Christoffel symbol. Easy enough, right? A plus sign. But this, of course, brings us right back to our central mystery. If we add a correction for the vectors with an upper index, why on earth do we subtract it for the other type of vector, the covariant ones with a lower index? What's going on? Well, the answer is just it's incredibly elegant, and it's not a random choice. It's rooted in a deep, fundamental principle of how the universe has to work. So let's get to the reveal. The solution to this whole thing doesn't come from some super complex calculation. It actually comes from a fundamental principle. Some things in the universe must remain constant. They have to be the same for every observer, no matter how you look at them or what coordinate system you use. We call a value like this a scalar invariant. And the best way to think about it is with an example like temperature. Imagine the temperature at a single point in space. It doesn't matter if you measure it in Celsius or Fahrenheit or Kelvin. You'll get different numbers, sure, but the underlying physical reality, the actual amount of heat energy at that spot, is the same for everyone. That physical reality is the scalar. It's a truth of the system. So here's the puzzle. It turns out we can create one of these perfect true scalars by combining our two different types of vectors. So now we've got a logical setup with two unbreakable rules. Rule number one, the derivative of a true scalar is simple. It doesn't need any correction term because it's already a truth. Rule number two, the product rule from calculus. Yeah, that one. It must always hold true, no exceptions. Both of these things have to be true at the same time. Okay, so let's just walk through the logic here. It's actually pretty cool. We start by saying that the derivative of our scalar, this a times v thing, is just a simple derivative because it's a scalar. No correction needed. But we also know the product rule has to apply, so we expand it out using the product rule. Now here's the key step. We already know the rule for the v vector, right? It gets a plus sign with its correction term, so we substitute that in. And the moment we do that, the whole equation is unbalanced. We're left with this extra positive term just floating around. So what's the only possible way to make it all work? To make both sides of the equation equal again? The only way is if the correction term for the a vector has an equal and opposite minus sign. It's not a choice. The math forces our hand. And that's really the heart of it. The minus sign is not some random convention that a mathematician just picked one day. It is a logical necessity. It's the only thing that works if you want the fundamental laws of calculus to stay consistent when you start dealing with curved space. It's there to make sure that the positive noise from one vector is perfectly canceled by the negative noise from its partner, so that the underlying truth, the scalar, remains unchanged for everyone.
So, solving this little puzzle wasn't just some abstract mathematical exercise. This logical necessity, this simple minus sign, is what unlocked our entire modern understanding of the universe.
I mean, just look at this timeline again. Christoffel figures out the math. A few decades later, Ricci and Levi-Civita package it all up into this brand new toolbox called tensor calculus. And then, in 1912, a mathematician, Marcel Grossmann, sees that his good friend is totally stuck on a physics problem he's been working on for years. And that friend's name was Albert Einstein. Grossmann showed him the toolbox.
And that was it. That was the breakthrough. Without this consistent set of rules, including our mysterious minus sign, Einstein could never have written his famous field equations. The language of modern cosmology would literally not exist. So think about it. General relativity, understanding gravity as the curvature of spacetime, the prediction of black holes, even the science that makes GPS navigation on your phone work. None of it would be possible without getting that minus sign right.
So, let's just quickly recap our little investigation. First, we had the problem. Simple derivatives break in curved space because the coordinate grid itself creates noise. Second, we found the tool, the Christoffel symbol, designed to perfectly measure and cancel that noise. Third, and most important, the logic. To keep a true value, a scalar, consistent, the positive correction for one kind of vector absolutely must be balanced by a negative correction for the other. It's the only way the laws of calculus hold up. And the result of all that? A brand new mathematical language, powerful enough to describe the entire universe.
It really makes you wonder, doesn't it? If a secret as profound as the nature of gravity was hidden behind a single minus sign in an equation, what other incredible truths about our reality are just sitting there, hidden in plain sight, encoded in the language of mathematics, just waiting for someone to come along and ask the right question? Thanks for joining this explainer.
All right, let's dive in. Today, we are opening up the case file on a 50-year mathematical detective story. A mystery that, once solved, completely unlocked the secrets of the universe. And right at the heart of it all is one of physics' most important formulas and one very stubborn, very crucial minus sign.
So here it is. This is the formula that tells us how things change in the curved, warped universe of general relativity. And you'll notice one version gets a plus sign and the other gets a minus. But why? I mean, why isn't it also a plus? This isn't just some random choice. It is a fundamental truth about how curved space actually works. And figuring out the answer took some of the greatest minds of the 19th century half a century to crack.
To even begin to understand the problem, you first have to understand the world where this problem lives. You see, for centuries, math pretty much happened on a flat piece of paper, a world where all the rules are simple and a direction is, well, absolute. But the universe, as it turns out, isn't flat. It's a world of curves, and that changes everything. Now, this wasn't some single eureka moment. It was a slow, careful construction, almost like a relay race of geniuses. It all started with Gauss, who had this brilliant idea. Imagine you're a two-dimensional creature living on a surface, completely unaware of a third dimension. Then, his student, Riemann, just blew that idea up to any dimension you can imagine. But the key, the real breakthrough, came from Christoffel. He's the guy who figured out how to make a correction factor for our changing rulers. And then finally, Ricci and Levi-Civita came along and packaged all of it up into one complete mathematical toolkit, one that would be sitting on a shelf, just waiting for Einstein about a decade later.
So, what was this huge problem they were all trying to solve? Well, it boils down to a single flaw in one of our most basic mathematical tools, the ordinary derivative. Let's go ahead and put our first suspect on the stand and see why it fails so spectacularly in a world full of curves.
In a flat Euclidean space, like a sheet of paper, life is simple. The direction up over here is the exact same as the direction up way over there. The little arrows that define our coordinate system, our basis vectors, they're constant. They never ever change no matter where you go. But now, just look at a sphere. The direction north at the equator is pointing in a completely different way than the direction north up near the pole. The very basis vectors that define our map are twisting and turning as we move. And this right here perfectly illustrates the central challenge. How in the world do you measure change when your ruler itself is changing under your feet? And that is the fatal flaw of the ordinary derivative. It was designed for a flat world, period. When you try to use it on a curved surface, it actually measures two things at the same time: the real physical change you care about and the artificial change that's just caused by the twisting of your coordinate system.
So the answers you get are frankly junk. They're not real, they're not true physical quantities because their value changes depending on whatever coordinate system you just happen to choose. It's like trying to measure the speed of a car that's on a spinning merry-go-round. The number you read is a mix of the car's actual speed and the speed of the platform itself. We need a way to subtract the platform's spin to find the real truth.
And this is where our hero enters the story. The mathematicians of the 19th century didn't just throw out the old derivative. No, they did something way more clever. They built a breathtakingly smart add-on. A precision tool designed specifically to listen for that mathematical noise and then cancel it out perfectly.
This is it, the Christoffel symbol. Now, don't worry about the crazy formula for it. Just think of it like a pair of noise-canceling headphones for math. It's a little machine that you feed your position on a curved surface, and it tells you exactly how much your coordinate system is twisting and stretching at that one precise spot. And so, the new improved tool, the covariant derivative, is just beautiful in its simplicity. It's nothing more than the old flawed derivative plus this new correction term we just built. The first part gives you the real change plus the noise. The second part comes in and subtracts that noise, leaving you with only the real physical change. It's perfect. Okay, now it turns out there are two flavors of vectors, and they transform in opposite ways. You can think of them like a push and a pull, or a yin and a yang. For the first type, called contravariant, these are things like velocity. We've seen that the correction term needs a plus sign to cancel the noise. But for the other type, the covariant vectors, what sign does their correction need? The answer to that is the key to our entire mystery. Okay, we have all the pieces on the board. We've got a flawed tool, a correction factor, and a mystery. And now for the climax. We are about to solve the secret of the minus sign, not with some complicated, messy calculation, but with a simple, inescapable piece of pure logic. The key that unlocks this entire puzzle is the scalar. A scalar is just a single number, like temperature or mass, and its value is absolute. The temperature in this room is what it is, right? It doesn't matter if you measure it in Celsius or Fahrenheit or Kelvin, your coordinate system is irrelevant. The number is real, it's absolute. And here's the crucial trick. You can actually build one of these rock-solid absolute scalars by combining our two different flavors of vectors, one contravariant and one covariant, in this very specific way. When you do that, the result is a value that will be the same for every single observer in every single coordinate system. This is our anchor to reality. And this leads to a logical checkmate. Let's just walk through it. Step 1. Since our combined object is a true scalar, its derivative has to be simple. It can't have any of those messy correction terms. Step 2, but we also know a basic rule from calculus, the product rule. To find the change of two things multiplied together, you have to account for the change in each part separately. And now step 3, the final move. We already know for a fact that the derivative of the v part gets a positive correction term. So for the total correction to add up to 0, which it must do for a scalar, the correction term for the a part has no choice. It absolutely must be negative.
That minus sign isn't an arbitrary mathematical convention. It's not a choice. It is a logical necessity. It is the only way for the math to work, for scalars to stay absolute, and for the laws of physics to be consistent no matter how you're looking at them. The case is closed.
So okay, a beautiful piece of logic solved a 19th century math puzzle. Awesome. But why does it matter to us today? Because this wasn't just some academic exercise. This was the key that would eventually unlock the entire cosmos. In 1912, Albert Einstein was completely stuck. He had this revolutionary, world-changing idea for general relativity, the idea that gravity is just the curvature of space-time, but he had no idea how to write it down mathematically. His friend Marcel Grossman pointed him to the work we've just been talking about, the fully developed tensor calculus, which was basically just sitting on a shelf waiting for him. And this is just a stunning example of the power of pure mathematics. The tools that were built by Gauss and Riemann and Christoffel really just out of sheer curiosity, they turned out to be the exact tools Einstein needed to write his field equations and to describe the very fabric of reality. That minus sign is woven into the structure of his theory. The legacy of that one little minus sign is just staggering. It underpins all of general relativity, which in turn predicted the existence of black holes and the expansion of the universe. And it's not just cosmic stuff, it's in your pocket.
The GPS on your phone relies on satellites moving really fast in a slightly weaker gravitational field. Well, according to relativity, that means their clocks tick just a little bit faster. If engineers didn't correct for this using the very math we've just discussed, your GPS location would drift off by several miles every single day.
So the next time you see a complex equation, remember this story. Remember the covariant derivative. Because sometimes the biggest secrets, from how black holes work to why your phone knows where you are hidden in plain sight, tucked away inside a single, essential, and very hard one minus sign. Makes you wonder, what else is out there, just waiting to be discovered?
All right, welcome to The Explainer. Today, we're going on a kind of mathematical detective mission. We're on the hunt for a secret, a really important one that's hidden in plain sight inside one of the most powerful formulas in modern physics.
Okay, take a look at this equation. This beast is called the covariant derivative. And our entire mystery today, the whole thing, boils down to that one tiny little symbol you see right there, the minus sign. Now, it might look like just a speck of dust, a minor detail, but I promise you, it is the absolute key to describing, well, everything, from how gravity works to the very shape of our universe.
So how do we crack this case? Well, to get the solution, we first have to understand the problem. You could even say we need to investigate the crime scene. And that crime scene is curved space. We have to ask, why do we even need this special kind of derivative in the first place? So that brings us to our first section, the problem with curves. This is all about why our normal everyday math just completely falls apart when things get bendy. Here it is. This is the heart of the issue. On the left, you've got flat space. Think of a simple sheet of graph paper. Your directions, your up and your right, they are the same no matter where you are on the page. Simple. But on the right, on a curved surface like a sphere, the whole grid stretches and warps. Your sense of what forward is changes with every single step you take. The things that are actually changing are called basis vectors. The easiest way to think about them is as your local compass directions, your north and east, right at the single point where you're standing. The problem is, in curved space, that compass seems to spin and twist as you move around. And that's exactly why a standard derivative gets so confused. It's trying to measure how much a vector is truly changing, but it can't tell the difference between the real change and the change that's just an illusion caused by the coordinate system shifting underneath. It ends up mixing the actual signal with a bunch of, well, you can call it coordinate noise. Okay, so if our math is getting garbage data, how do we fix it? How do we clean it up? Well, that brings us to the next step, the correction factor. We need essentially a noise-canceling tool for mathematics. Now, this fix didn't just appear overnight. It was built on the shoulders of giants. It started with the legendary Carl Friedrich Gauss, who imagined what it would be like to be a two-dimensional creature living on a surface. Then Bernard Riemann came along and just blew that idea up into any dimension you can imagine. But the person who finally put it all together and invented the perfect tool for our specific problem was a German mathematician named Erwin Christoffel in 1869. And he called it the Christoffel symbol. Its one and only job is to perfectly capture that coordinate noise we were just talking about. It's a term that knows exactly how your grid is stretching and warping. It basically distills all that noise into a single object so we can finally subtract it out and get to the real physical truth. But here's where it gets a little weird. It turns out there are two fundamental flavors of vectors. For the first kind, called contravariant vectors, and you can think of these as arrow-like things, like velocity, the math shows the coordinate noise has a positive sign. So to cancel it out, you just add a correction term using that Christoffel symbol. Problem solved, right? Well, not quite. And this brings us right back to square one, to our central mystery. If we add the correction for that first type of vector, why on earth do we subtract it for the other type, the covariant vectors? The answer, it turns out, isn't some random choice. It's incredibly elegant, and it points to a really deep truth about the very rules of the universe. Okay, here we go. The reveal. We are going to solve this thing, and the solution doesn't come from some monstrous page-long calculation. It comes from a simple, fundamental principle. Some things in physics must be constant, no matter who is looking or what weird coordinate system they're using. That thing is called a scalar, or a scalar invariant. It's just a single value that all observers have to agree on. It's a truth of the system. The temperature at a specific point in a room is a perfect example, right? It has one real value. It doesn't matter if you measure in Celsius or Fahrenheit, or if your grid is skewed, the underlying physical reality of that temperature is the same for everyone. It's invariant.
So here's the absolute masterstroke. It turns out you can create one of these perfect invariant scalars by pairing our two different types of vectors together. And doing that sets up a little puzzle with two unbreakable rules. Rule 1, because our scalar is a true value, its special derivative doesn't need any correction at all. And rule 2, the product rule, the one from basic calculus, it has to hold true. It's a fundamental law of math. Both of these things must be true at the same time.
So let's just walk through the logic. We start with our scalar knowing its derivative is clean, no correction needed. Then we apply the product rule, which you see on that second line. Now we have to deal with the individual vector derivatives. And this is the key. We substitute in the correction for the v vector, the one we already know has a plus sign. And for the two sides of that equation to stay equal, for everything to balance, the correction for the a vector is forced to have an equal and opposite term. It has to be a minus sign. There is literally no other choice. So you see, the minus sign isn't just an arbitrary choice somebody made. It's a logical necessity. It's there for one reason, to perfectly cancel out the plus noise coming from its partner vector. It's this beautiful mathematical teamwork that makes sure the overall scalar truth, the real physics, remains unchanged. So what, right? We solved a little puzzle about a minus sign. It's a neat trick. But this wasn't just some abstract mathematical exercise. It turned out to be the key that unlocked the language of the entire universe. Christoffel's brilliant idea was taken by a couple of Italian mathematicians, Ricci and Levi-Civita, and systemized into a powerful new toolbox called tensor calculus. Then, flash forward to 1912. Albert Einstein is tearing his hair out trying to describe gravity as geometry, but he doesn't have the right math. His good friend, a mathematician named Marcel Grossmann, shows him this exact toolbox. It was the missing piece he'd been looking for. I mean, just look at what this math made possible. Without this complete set of rules, including our logically necessary minus sign, Einstein could never have written his field equations. The language of modern cosmology just wouldn't exist. The GPS in your phone, which has to constantly account for space-time being curved by Earth's gravity, relies on this math being exactly right, down to the last plus or minus sign. So let's just do a quick recap of the clues we followed to solve this mathematical mystery. It's a pretty cool story. We started with a fundamental problem. Derivatives were broken in curved space. We found the perfect tool, the Christoffel symbol, to measure and quantify the noise from the coordinates. And then, just by insisting that the basic laws of calculus must always hold true, we uncovered why that minus sign isn't just correct, it's absolutely essential. And the result of all that logic was a brand new language, one capable of describing our universe. It really makes you wonder, doesn't it? What other huge secrets about how our reality works are just sitting there, encoded in the language of mathematics, just waiting for us to ask the right questions? Thanks for joining us on The Explainer.